Okay, good morning, everyone. So I think we should start this workshop today. I'm Tomasz Kryjak from AGH University in Poland, and with us is also Andrea Pinna from University Sorbonne of Paris, and we both organized this workshop. DASIP, as most of you probably know, has a quite long history. It's now the 14th edition of this workshop. However, the first time in conjunction with DASIP. Previously, it was, as far as I know, it started as a conference, and then it was it started as a workshop, then it was transferred to a so-called standalone conference, and now it's, due to several reasons, again, a workshop. We can discuss these reasons then in the afternoon session. Just in the beginning, a very quick statistics and how the review process looked like for this workshop. So we got in total 17 submissions. Here, the first number is the number of submissions. The fractions are due to that several papers were co-authored different countries. Example, some papers from France were co-authored with Tunisia. So it sums up to 1 to 6 here in this case. So the most papers were, and the second number in brackets is the number of authors. From France, Poland, Germany, Netherlands, Greece, Canada, India, Tunisia, and Finland. So I can say it's an international conference and workshop. Every paper was reviewed by at least 3 members of our technical committee. Some even got 6 reviews, the most 4 or 5, I suppose. In total, 72 reviews were made, and here at this point, many thanks to all the TCP members who are present here and who are not present, because they did good work. We had a tight schedule. There was 2 or 3 weeks in total for the reviews, and they did their job great. So based on the reviews, we as the program chairs also and consulted this decision with the steering committee. We accepted 9 papers, which will be presented today, and these papers will be also included in the ICM proceedings. Also, what is a nice thing, the extended version of all of these papers were invited to a special issue of a Journal of Signal Processing Systems. Of course, here assuming that they will get another positive review, because as an extended version, they will have to be reviewed again. The schedule is available on the HiPEC website also. I hope you did get your by email due to the via the EasyChair system. So I don't want to get through it. We will start just in a minute with Keynote by Diana Göhringer, and then we will have 3 sessions. It's divided by a lunch and HiPEC keynote, and the last we will finish with a discussion in the end. Here, just about the discussion session, because it's something not typical. So first of all, please keep, I'm talking now to the speakers, please keep the timing, the 15-minute presentations, and then 5 minutes for a short Q&A, because as you can see, the schedule is rather tight. We have rather short breaks, only 10-15 minutes. Only the lunch break is 1 hour. So we have a rather low margin if something goes wrong. And also, hopefully not, but there is always the possibility for some technical issues. So, so please just keep the timing. And the second issue is that after this whole 3 sessions, we have a 2-hour slot. Initially, we planned a keynote, but it turned out that we have time for discussion. So I will provide a link to a document. I think I will do it via the chat, but because I don't have maybe I can figure out how to send an emails to all attendees of this workshop. So then we can, it's structured almost like the schedule. So each schedule has a page, each presentation has a page, and then you can write questions there to particular papers if you weren't able to ask the questions just after the presentation. So then we can have a discussion without limits, and that's for the keynote and also for the track papers. And in the end, there is also a general page, so we can ask other questions. One question, I've started this, there are already 3 questions by me. Here in the scope of DASIP, it's, for example, how we could in the future as a community improve the number of submissions. For example, was it this year due to the COVID pandemic and all the issues related to it, or is it a more constant trend that this conference, and as I observe, all conferences have some problems with the number of submissions. So here, just we can do an Q&A without very strict time limits. So for me, it's having a good and inspiring workshop. Andrea, do you want to add something to this?
No, thanks, Thomas. Just say welcome to everybody, and it's I think it would be a pleasure to listen and after speak together about this interesting and these topics. Thank you.
Okay, so we can start with our keynote. Diana, are you ready?
Yes, I will try to share the screen.
Okay, so, but just let me then to introduce you.
Okay.
Okay, so it's my great pleasure to introduce Diana Göhringer, who agreed to give a keynote today about concepts and realization for a configurable domain-specific multiprocessor system on chip. I assume most of us know Diana, but in case no, then Diana is a professor for adaptive dynamic system at Technical University of Dresden, Germany. From 2013 to 2017, she was an assistant professor and head of the application-specific multi-core architectures research group at Ruhr University Bochum in Germany. And before that, she was working as a young investigation group, CADIMA, Computer-Aided Design and Exploration of Multi-Core Architectures, and the Institute for Data Processing and Electronics at Karlsruhe Institute and Technology. Before, she was also a senior scientist at the Fraunhofer Institute of Optronic System Technologies and Image Exploration in Ettingen, Germany. She obtained her PhD in 2011 in Electrical Engineering and Information Technology from the Karlsruhe Institute of Technology, summa cum laude, so excellent. She's the author or co-author of over 130 publications in internal journals, conferences, and workshops. She serves as a technical program committee member in several international conferences and workshops. She's also involved in this year FPL. She is a reviewer and guest editor of several international journals. Her research interests include reconfigurable computing, the processor system on chip, networks on chip, simulators and virtual platforms, as well as hardware, software co-design and parallel programming methods. So the floor or the microphone is yours. Hello? Diana, do you? We cannot hear you.
I don't know if I write some message, but I think that she can't. Yeah.
Is it working now?
Now, yes.
Yes.
Now,
okay.
Yeah, it's going. Yeah.
Good. Yes, it's the headphones somewhat hanged up, so perfect. Thank you. But I will come up. So well, it's my pleasure to be here and to give you a little bit an overview about some concepts and some realizations which we did for reconfigurable and domain-specific multiprocessor systems on chips. So the outline for the talk will be, first I want to give a short introduction about the chair. Then I would like to give an introduction on the topic and motivation, why reconfigurable as well as domain-specific MP-SOCs are so interesting. I will give a short system overview, some examples of possible processing elements, some which we used, some which others are using, and also about, well, processing elements are not the only important thing, but you of course also have to look at the network on chip. And also, as we saw in the keynote on Monday, now memory of course is also important. And furthermore, how to program such a system, and then to give some application examples in relation to one of our research projects. And finally, a conclusion and an outlook. Well, so as we are all virtual, unfortunately, we could not go to the original location of the conference here. We are in Dresden, so just very close from Berlin to ours by car or train. Nice city on the river Elbe. And you see here the Frauenkirche and some view on the city center. This is the campus of the university. As you see, we have some old and new buildings. Currently, it's very empty. I'm also at home at the moment. And up here are some fields. So here we use the place to test our drones. And up there is also the computer science faculty building. My group consists of 12 PhD students and 1 postdoc. And we are focusing on domain-specific computer architectures, hardware software co-design, and of course also how to program them and manage them at runtime. And I will focus the talk mainly on the architectures and the tools. And I will introduce, so those are the current projects which we are running at the chair. And I will focus mainly on Marie, but also give a short outlook what we do in SETI and SNFBot. And the applications for which we do the systems, so we are focusing mainly on image and signal processing algorithms. So those are the domains which we are targeting, mainly from robotics, but also automotive applications. So if you want to make some automotive systems or adaptive systems like autonomous cars or autonomous robots, where we have an increasing complexity. We have mixed criticality requirements, real-time requirements, so we need to brake on time, for example, if somebody runs over the street. On the same time, especially for a robot, we have to have a low power and energy consumption, so the thing should be mobile and not always connected to a power supply. Also, the size of the computing platform should be small, and it should be able to adapt to changing environments, which means, for example, if you have such a robot like this Pepper here, and you put him in a different building, he also should find his way and be able to move around. This cannot be solved by just having a single core solution. A possible solution widely used are domain-specific MPSOCs or heterogeneous MPSOCs. So where you have a system which is optimized for the specific application domain. It should support dynamic behavior. And the question is just migrating software tasks to other parts of the system sufficient? And I'm a strong believer that we need also to have some way of adaptivity, not only from the software, but also from the hardware. And therefore, from my perspective, reconfigurable domain-specific MPSOCs are a better solution because we can adapt both hardware and software to the requirements, which means we can load new hardware accelerators to the system and provide this way an energy efficient solution for each application phase. So how can such a system look like? What are possible processing elements? From abstract view, most reconfigurable multiprocessor system on chips, which you find, not only ours, you have an FPGA platform, which allows you to use some partial reconfiguration. You have such a system here with, in this example, it's a network on chip, but often people also just use a bus system. And we have different processing elements, so processors, different kinds, and also dedicated hardware accelerators, for example, to detect a car, do some image processing or machine learning application. And of course, memory blocks on chip as well as off chip. If two partners are now communicating, we can change the hardware of our system. So add a hardware accelerator instead of the CPU, which was there before interrupting the rest of the system. We could remove or shut off some parts of the hardware to save energy. And we also could add new accelerators as runtime, so extend our system to provide a higher performance. Furthermore, we could add, let's say, also not only the processing elements, but also change the communication infrastructure. Like here, if we need a higher bandwidth to the memory, we could increase that, for example, also using partial reconfiguration. And the advantages are that we have a very high flexibility, which means we can adapt both hardware and software to the application requirements. We can achieve, therefore, a high performance per watt, as we have application-specific architecture, not only at design time, but also at runtime. And furthermore, we have more functionality on a small chip. So let's say, assuming you want to have all possibilities on the FPGA online and just turn it on and off, then you would need a big chip. What we rather do is we use the same resources for different parts at different times. And therefore, we can go for a smaller chip, which reduces our costs and also our power and energy. What are typical processing elements? For example, of course, we need some processors in our system. If we go for Xilinx, we can use a microplace, which is very optimized for it. But of course, it's yes, it's not open source. So if you wanted to move to a different vendor or build your own chip, then you have to exchange it. There are many open source processors available. Here are just some examples: Risky, Tiger, or Rocket Chip, from 32 bits to 64 bits, different interfaces. And as I think most of you know that the RISC-V toolchain there are a lot of open source components. And we used so for microplace and Risky of those which are here in the table. Of course, we also need some accelerators. So of course you can make a dedicated hardware accelerator, or you could think of something more flexible, a bit more programmable. For example, here is a GPU, which is from Michael Hübner's group in PTU Cottbus. It's also open source, so everybody can use it. And basically you can think of it as a GPU, which you can put on an FPGA and which you then can connect to your processing system and program it with OpenCL to execute some machine learning workloads and other throughput-oriented workloads, which are good for GPUs. And it's configurable. You can select how many number of cores, for example, you would like to have. So if you have different processing elements, the next question is, what can we do with the network on chip? So with the interconnect, because you need it, but why not use it also for doing some processing? Like you can do processing in a memory, why not only also do processing in a network? So if you have a normal system with processing elements and some routers, basically you send a message from one end to the other, and the message has a header, some data, and a tail. And it's basically just transferred to the receiving end. And then the next processing element is doing the processing. Often you have some very simple or basic tasks to do. And the idea is, why not do them in the network on chip, right? So when you transfer your message, if you have a special router here, the router can already do some processing of that message before shifting it to the next router. And this way, you already use the time by transferring to do some processing of it. And finally, the more complex processing can be done by the processing element itself. What do we have to change to allow that we can do some processing in a router? Basically, here you see a normal network on chip. You see a normal router here, and with a crossbar, some routing, some arbiters, and some buffers. And what we change are the buffers. So we added there processing units so that we can do some processing of it. And this is how it looks like. So usually Axis Stream is basically a FIFO-based connection which we use. And this is the standard way over this buffer. And if the message has a specific header, which we analyze, then we can show, okay, it's an instruction message. So we should do some processing, which can be done then on this path in the router. And the system is done in such a way that the complete function here you can program in a hardware description language like VHDL, but it can also be programmed in a high-level synthesis approach using C and C++. And it's good for basic, simple processing applications so that you can process it while it's streamed through, because otherwise you would lose too much time in a router. And here is a simple example of some image processing application which we explored. We had a system with 3 microplace processors. A single microplace needs for the whole application, which was just some RGB to gray transformation, some Sobel filter, and some thresholding. this amount of time for an image of 640 by 480 pixels. So assuming you speed it up you distribute it ideally on 3 processing elements, you would expect the execution time on 0.38 seconds. So speed up of 3x. And as we see here, the results of a normal MPSOC with a network on chip, which is just used for transferring. And on the right side, we see an MPSOC where we do the in-network processing. The communication overhead is shrinking. It's still there, it's not 0, but it's less, and we can save around 42.8% for that application. So when we have a hardware architecture, what are possible ways to program it? You need some program methodology. That's the one we are using. Basically, at the bottom, what we want to have a reconfigurable system. So we need some full and partial FPGA bit streams. We need some software binaries to run on the processors or on an accelerator like the FGPU. And we need basically a task graph and a layer description for runtime system. Our input, we target image processing applications, and we are using the OpenVX standard. So mainly start here. We have a special library for image processing applications, which is open source, which is called HiFlipVX. And I will introduce that in a moment. Basically, you can write in your application in C, C++ or OpenCL and use then our application partitioning and mapping tool, which will decide where to execute which part of the application. We also have a simulator, System C simulator, where you can simulate your application and test it. This is very useful to do it before you really go down to the chip, because it takes a lot of time. And this way you can do a faster design space exploration. In gray are commercial tools. So of course we use mainly Xilinx FPGA, so we need the Xilinx tools to generate our bit streams. And the tool we have here is just if you want to have some relocatable bit streams, which means we can move a bit stream from one area of the FPGA to another area of the FPGA. Of course, many people are also using MATLAB applications for image processing. And there's the real-time workshop within MATLAB where you can transfer MATLAB code to C code. So then you could use it here as well. With some modifications, of course, it's not a fully automatic approach. Due to the time, I will just focus on 2 parts of it. But if you have questions to the others, I'm more than happy to answer. So I would start with the HiFlipVX library, because I think that fits best to DASIP, but it's a library focusing on image processing. It's open source, so please feel free to download it and try it out. The current version, which we're currently working on, includes 46 image processing functions, as well as 7 neural network functions, so like convolution layers and so on. It's parameterizable and optimized for high-level synthesis. We mainly optimize it for the Xilinx tool, so Vivado HLS, but in collaboration with other partners, there's also a part of it transferred already and tested with Intel FPGAs. The functions are based on the OpenVX specification, so we would wanted to have a standard here. It also gives us a good task graph, which we then later on can use to place the design on our MPSOC architecture. It supports auto-vectorization and different types of data types, and also different kernel sizes for filters like Sobel and others. Here are some examples of some of the functions available: basic pixel-wise operations, like arithmetic addition, magnitude calculations, for example. We have image filter functions like Gaussian filter, Sobel filter, convolution, of course, and dilation, erosion. Furthermore, we have image conversion and analysis functions, like to make an integral image or a histogram, and others also to scale an image. The features of the library are that we have a very good scalability. We have a low resource usage. So for example, in this figure, you see the comparison of some of our filters with XFOpenCV, the library from Xilinx. And the dark ones are the flip-flops and light gray ones are the lookup tables. So we usually need less resources here. So we can save some hardware resources. The standard configuration, which is mentioned here, is a vectorization of 1 and the kernel size of 1, as well as a data type of 8-bit. Here you see the scalability. So if we increase, for example, the kernel size, we need, of course, more resources, but it scales linear. Same for the vector size or different data types like 16 or 32 bits. Here are some examples of our resources which we need. For example, histogram of 8 bits needs only around 600 lookup tables, 2 VRAMs, and 113 flip-flops. So after we have described our application with 5 flip-weeks, with the library, we can use the application partitioning and mapping tool to decide how many cores we need and how to partition it. And the idea what we want to do is we have a task interaction graph. So we have a graph of our application, and I will show a more detailed example later. And we need a model of our platform. For example, here our MPSOC system with 4 areas. I also call them in the following partitions. And we want to map this one here, then here, such that we avoid a lot of communication here between the different partitions. And we also have a good balance of each of them. The partitioning, so the creation of the task is done by the developer. It's done basically if you use OpenWX automatically by those functions. And clustering and mapping are, just as a reminder, NP hard problems. So we work here with heuristics to parallelize and map our applications. Just to give you an idea, if you have 9 partitions and 24 tasks, that would result in 9 up to 24 different mapping solutions. And basically, this is how the algorithm is working. We start with an initial graph and then optimize it further doing load balancing. And as you see here, those are the different tasks. They are bound with each other, which are showing the communication between them. And it works like basically a rubber. So unweighted edges are forced together like a rubber. And on the other side, the tasks are forced apart from each other based on the capacity utilization. What you want to optimize is, on the one side, the dilation. So we would not like to have something like this, because then we need to communicate, for example, over those 2 ways, have a 2-hop communication, but rather place them closer to each other, because otherwise we need that link and this link. Furthermore, we want to avoid something like we see here. For example, we have a lot computation here, and this one has nearly nothing to do. So also there to do a good load balance. And the algorithm is based on several optimization heuristics. So it uses taboo search, simulated annealing, and gradient descent. And further, it's parallelized, so it's executing different solutions and in multiple threads. And it can support different topologies. So you don't only need to use it for an MP-SOC. We originally used it for an FPGA cluster system, which means where each of those partitions was not a processing element or an accelerator. Originally, it was a whole FPGA connected with other FPGAs. And here are some computation times. And as you see, it scales linear, the more nodes we get. So it allows a fast computation of different mappings. Yeah, so far to design and programming methodologies. And in the next, I want to show you how to apply such approaches to real applications. And we are part of a national research project. I think you can see the animation. Yes, it's called Marie. It started in 2017. It's a DFG National Science Foundation from Germany project. Transregio, which means between different universities. It's led by University Duisburg-Essen. And we are now in the second phase. The idea of the project is that we have such a flying robot or drone, and it can basically analyze the room and make a material map of the room. There are different research objectives. On the one side, how to do the material characterization, how to localize the drone, so more on the signal processing applications, but also, of course, the sensors to do that. So terahertz sensors are also investigated, how to make them and how to make them small that they fit on a drone. Our contribution is to have the computing architecture, which will be later on the mobile robot. So to have a domain-specific computing architecture, and also how to make it programmable, so that at the end we can use the drone to fly through that room and to make in real time a material map. The architecture, the first draft looks like this. So we have several routers. We have so-called processing clusters. So we not have only one processing element here, but we have a cluster of up to 4 cores at the moment, which communicate over shared memory with each other. Or we use a dedicated hardware accelerator, either in the cluster like here, or separate. And for the cores, as the later goal, so that project is now in the second phase, it can have up to 3 phases. So there can be 4 additional years, will be to make a chip. So therefore we are using here the RISC-V core, and we are using RISC-E at the moment. And this is the layout of the system. As you saw, it has a 3x3 network on chip. And on each corner we have 4 processing elements, so 4 processors. So this is the final layout. The network on chip is placed here on the FPGA, and those are the clusters with 4 cores each. So we basically have 36 cores on this FPGA at the moment. And we also support to do partial reconfiguration of the cores to add a dedicated accelerator. And we are currently looking at to add also such a GPU-based accelerator here. For the resources, we see some examples here. So, and we are not the only one working on such a cluster-based MP-SOC. At the bottom, not sure if the pointer is pretty good working. You see our architecture. So you see the FPGA we are using is quite big. It's a Vertex Ultra scale. It's hard to compare all of them with each other because, as you see from the RISC-V ISA, we all use different ones. We use the same as Hero, which is a RB32 IMC version, but we only have 4 processing elements. Per cluster, they have 8. And we support less memory. From the power consumption, we are more or less similar to ESP. And from the frequency, we are in a moderate range. So we achieve on the vertex alter scale, currently for the architecture, 120 megahertz. And so how we support the programming of that architecture, this is basically shown here. Here under A, you see the application model, which is the task graph, which we saw before. And here you see the platform model consisting of the routers and the partitions where we want to place it, as well as the links where we want to avoid that there's a lot of communication about them. And then in step C, we get first an intermediate architecture, which means a decision what should be an accelerator, what will be a processing element. And then finally, in the mapping happens where we place the elements in the specific partitions. What we see here is also something I didn't show before. It's a primary. So we can have a system fully controlled by hardware. So we have also some, in HiFlyPX, some network on chip functionalities to control the network directly, and that we can have accelerators directly connected to the network on chip without the need of a processing element. So we don't necessarily need to have a processor here, if it helps to save some energy and increases the performance of the system. So now let's see if that video works. So this is how we apply the architecture, and just to give an outlook of other systems which we're using, and I think from the time I'm good, so I can show it. It's just a short teaser video which we presented at 5G Summit, and there you can also find the full one. Okay, the audio doesn't work. Interesting.
Investigating novel hardware software concepts for domain-specific as well as self-adaptive single and multi-core systems. We evaluate our designs of different applications such as image and signal processing algorithms from robotics, automotive, or Industry 4.0. And in today's video, we want to show you demonstrations from 3 of our research projects. The first one will be given by Sergio Petros, who will show you a robot Hubert demonstration of our Pepper robot, which we built for the City Cluster of Excellence. Cornelia Wolf will present the final results of the SysKit project, which targets Industry 4.0 applications. And finally, Peter Mamini-Rath will present you one of our flying robots, which is designed for the SnitBot project. Thank you very much for watching. If you have any questions, please feel free to contact us and enjoy the video.
Yeah, so this was just the teaser video, and I just wanted to show that at the end, we would like to have, of course, the systems on such a flying drone. At the moment, we are using a pink platform here, and in the other projects like CETI, we are working with the Pepper robot, which you saw a little bit in the figure. And also for this, we want to have some application-specific architectures. So this was just a teaser video, as the other one is a bit long, but it's still available on the website of the 5G Summit. And so this to give you some idea about some application examples. And finally, just I would like to give some conclusion and an outlook, and then I'm more than happy to answer any questions you might have. As a summary, what I wanted to present are the benefits of using, or better, combining domain-specific as well as reconfigurability for multiprocessor systems on chips, because this way we have a high flexibility as we can adapt both hardware and software at design as well as at runtime to the application requirements, which can be data throughput, real-time, safety, and others. I mainly showed some examples for image and signal processing domains, which are the domains we are targeting. We can achieve this way high performance, as we can have dedicated accelerators combined with processing elements for flexibility. Furthermore, we can have a high energy efficiency, as we have only on-demand functionality. So we reuse the same FPGA hardware at different time steps with different applications. And therefore, we have a better area utilization. And of course, if you do such an architecture, it's very important to think about how to program it. So to have some tool support. And we target this by focusing on the application partitioning and mapping, and also by providing entrance application, which means HiFlipVX library targeting specifically image and signal processing. As an outlook, of course, we are working on further architecture components. As I mentioned, we want to integrate that FGPU platform, for example, into our platform. We are focusing on other design methods and tools to more automatize it. We are continuously adding new library functions for HiFlipVX. So let's say 1 year ago, we only had 28 functions. Now we already have 46 plus 7 for the neural networks. So we are continuously improving that to provide more features. And furthermore, which I didn't present it due to time, we are also looking at how to manage such a system at runtime. So who is making the decision to adapt the system based on what input and outputs. And of course, evaluation with further applications. Well, and that's all from my side. Of course, what I presented was done from the team, which you see up here. And yes, as Thomas mentioned, I'm organizing next year's FPL. So if you want to, the website is up. You can scan the barcode if you want. I usually would distribute the flying call for papers at a conference, but as it's virtual, I thought I'd do it this way. Yes, hope to see some of you there, hopefully physically, we don't know, maybe virtual. Thank you. That's all from my side. Are there any questions? So I can see something in the F&A, or Thomas, you want to, or I'm not sure if I can see everything.
There is a question in the, you can see, Jana?
Yes, I can see one. Okay, so so there is a question from Markus Weinhardt. I'm not sure if everybody can see it. So how is the runtime reconfiguration in your MPSOC? Which means replacing a processor by dedicated hardware performed using Vivado or special methods. So we use Vivado for if we use partial reconfiguration. We use Vivado. We only use special methods if we use relocation. For this, we had the repabit tool. But that's only if you want to relocate, so which means just using the same bit stream for different plays on the FPGA. But basically, if you just do normal partial reconfiguration, having a dedicated to generate the partial bit streams, we use the Xilinx Vivado tool. Thank you. Any other questions?
Jana, I have a question. How you imagine you see the future if you take into account the last chip that Xilinx made to do AI implementation with a different architecture, that we have mixed hardware processor and reconfigurable architecture for accelerate computing and the dedicated processor for AI implementation, and how we can manage at the same time the complexity from the point of view of the algorithm, and at the same time the complexity of the hardware architecture, take into account that compiling some very easy algorithm can take now a lot of time. So there is a way that we can imagine the conception in order to reduce, to have a short compilation time.
So I hope, so that the question is how we manage the more heterogeneous hardware from next Xilinx platforms, right?
Yeah, not all. Yeah, Xilinx is just for an example, but everywhere say it's how we can, yes, we can manage the complexity from hardware and software point of view in order to don't disclose the compiling time.
Yes, I think it will be very challenging. So I'm looking to work with the new platform from Xilinx, which will be even more heterogeneous with the special cores for machine learning. But I think a big part of the work will be done how to partition the application. So how to decide where to run which part of the application, because the design space gets bigger and bigger. Let's say a homogeneous system to program is much easier. You just partition it, they're all the same. But for heterogeneous, yes, you have to think about how to partition it. And I think it will become very important to have a common input language, so which makes it easier to change decisions. So that, let's say if you have a VHDL plus C code, for example, it's very hard to move the VHDL back to run on the processor, something like this. So I think that would be probably the next step, or where there are a lot of research should be done, how to make it easier for the programmer to decide where to execute which part of the code and to automatically parallelize it in some sort. There are different approaches, and I know different companies are looking at that, and also research groups, but it's still not a finished issue. So let's say to parallelize that, to look into the compiler, to also have dedicated and special hardware considered there.
Thank you very much.
You're welcome. Thank you. Okay, there's a question about the processing inside the NOC routers from Marcelo Ruaro. So he asks about the cost in power and area. So yes, we need more area. It depends how much we do there. So in this example, we had, for example, if it's just a simple threshold, that will not cost much resources. If you would put a more complex algorithm there, like a Sobel filter or something like this, then of course you have to add the resources for that IP core in there as well. So you need to make a trade-off how much it works. The best from our side, the best things you could process in a NOC router would be things which don't need a lot of processing time, so just a cycle or two, and can be processed fast. And ideally, maybe also parts of instructions which reduce the message length, for example. Like if you have to make a sum of multiple elements, those would be very beneficial. More complex it would be if you would need, for example, two messages to combine them, let's say two matrices to do some matrix multiplication, then it would get much more complicated to make a decision here. So those would be some examples. So there's a trade-off. I would not put, let's say, a whole processor inside. That would be really big. If it's a NOC used as for an MP-SOC, because then you basically have a processor there, but it's good for, let's say, simple and small application tasks, like simple additions, multiplications, and those kind of approaches. Hope that answers the questions. So from the power, it's not a big part. And from the area, it strongly depends what's put inside. Okay. There's a question from Kevin Martin. So thank you. I also wish we would meet directly. Long time. Corona lasts longer than expected. So he's asking, the community has studied a lot about reconfigurable computing units, but now the problem is memory. What are the challenges in designing reconfigurable memories? Well, will be very challenging. I have not worked in the area, so like reconfigure memory, what has been done on the FPGA side is, of course, just reconfiguring the content of the BRAMs, which is possible. So you can exchange that part. You could, of course, use lookup tables to build a memory and reconfigure this one. But it will be interesting to see how that would be evolved. For example, how to combine the reconfigurability together with the processing in memory, or to have some reconfigurable layer in such kind of approaches. That I think would be very interesting, that you can basically exchange the functionality you have there so that you can support different kinds of processing in such memories. But I think also this is still an open research question, but a very interesting one. So I hope that answers these questions, more or less. So that strongly depends also on the target technology used for such memories. Okay, any other questions, comments? Okay, doesn't seem to be the case. Well, then thank you all. There's something in the chat. Oops. Okay, so in the chat, there's also a link for questions for the later Q&A, I just see.
Yes, thank you, Diana. Sorry, I had a slight problem with the internet, but now I'm back online, and therefore I cannot come up with a question because I was struggling to get back online.
No problem.
It's funny because I was just answering an email to Oğuz. It's good, I think, because he said that he would expect some problems with the internet connection, and I've got the problems. it's not so.
Just to interject for a second, sorry. It's even worse because the power is also out and I'm working on a laptop, so I don't know how this is going to go. It's like, oh, you have the workshop. Okay, let's now make sure it does not happen. That's what they're trying. So hopefully it will work out. Sorry about that.
Yes, it's we have now very strong dependent on technology.
Unfortunately, yes.
I would, for you, I could propose, I don't know, shifting the schedule, but hopefully, but because it's a workshop for more attendees, I do not know if we could do something like this, just in case you don't get your electricity back.
I think I can hopefully manage it. The battery is still pretty full, but okay. You know, since the whole universe is conspiring against me right now, I'm trying to be a little bit hopeful.
Should be safe. You should have an emergency generator and fuel. No, it's it's a little off topic, but for example, there was recently a quite short but severe breakdown of the all Google docs and presentations and so on, and it was like, oops, because more and more people have all the things online, and then in some point where it's no access, then we have slightly trouble. But
yes.
hopefully, okay. I think we can do the two following things, or freely discuss, or have a short break till 10:50, just to keep the schedule in case of some other attendees would aim on a specific talk. Okay, I think we can slowly start. There is still 1 minute left. The presentation is ready. The presenter is ready. So I would like to introduce Fritjof Steinert. He's been working as a research associate at the Fraunhofer in Heinrich Hertz Institute in Berlin since 2012. In this year, he obtained his Master of Engineering degree from the Beuth University of Applied Science in Berlin, and his research interests include the use of hardware accelerator technologies in data centers and their design, especially for image processing. The audience is yours.
Hello, thank you very much for your kind introduction. I will start directly with my presentation. First, I will give you a short overview of my presentation. I will start with our use case and derive the requirements for our system architecture from it. Then I will present the influence of the video quality on machine learning algorithms. Afterwards, I will present the influence Afterwards, I will discuss the effects of the coding latency. Next, I will present our low latency video coding. And then I would like to discuss the peak signal noise ratio curves. Finally, I will summarize our research and give an outlook on our future work. But first, to our application. Our goal is to detect shipwrecked people in the water as first step as a successful sea rescue operation. We want to use an unmanned aerial vehicle with a long flight duration and an HD camera for this purpose. The bandwidth to the ground station is very limited, especially with an increasing distance, which can be up to 100 kilometers. At the ground station, an operator searches for people in the water, supported by machine learning for object detection. The proposed processing pipeline from left to right consists of first the camera, then the image, the region of interest generation with simple machine learning methods, then the encoder, with region of interest, the wireless transmission to the ground station, the decoder at the ground station, and a more complex image classification with machine learning methods. Several requirements derived from the scenarios. First, real-time processing is necessary because the camera continuously streams video data. A second, rate control should be used because the available bandwidth should be used as best as possible for good video quality. So we must ensure that the encoded video data does not exceed a defined bandwidth. The third requirement is that interesting regions should be detected in the UOV and encoded with better quality, since machine learning requires few coding artifacts for a high detection rate. Our next requirement is that low latency encoding is used so that regions of interest set manually by an operator cause the time change of the encoded video. The system is intended to run on low-end FPGAs and therefore needs a low complexity. And we need also to transmit the entry image to be able to manually detect shipwrecked persons that are not automatically detected due to the simple machine learning algorithm in the UAV. With the following example, we want to show the impact of lossy video coding on complex image processing algorithms. In our use case, a machine learning algorithm operates on the decoded video. The display clearly pictures a kangaroo. For this example, we have encoded the image with different Pearson Rs, here with 33 decibel using the baseline profile. The second image is encoded with Pearson R of 26 decibel. Some coding artifacts are already visible. The last image is encoding with a Pearson R of only 22 decibel. The coding artifacts have increased significantly. A human can now have trouble recognizing the kangaroo. The three different images lead to different recognition rates on an ImageNet trained MobileNet version 2 deep convolutional neural network. In the table, we have shown the top three predictions. For the uncoded original image, the apparent correct prediction of a kangaroo is made in the first rank with a 99% probability. But already for the high quality coded images with 33 decibel Pearson R, the probability drops down to 60%. In contrast, neither the 26 decibel Pearson R image nor the 22 decibel image shows the correct prediction kangaroo in the top three list. Instead, there is a 7.8 probability of a hairless Mexican or a 16% probability of a battle tank. This short example clearly shows the impact of coding artifacts on object recognition. This is the reason why image regions of interest for particular applications should be encoded with a higher image quality. In addition to the video quality, the coding latency is the most relevant parameter. The latency is important for applications where an interaction between the receiver and the transmitter side takes place. Latency much lower than 1 frame period are required, which could be in the range of only several milliseconds. The first contribution to the total latency has the video input, typically a camera. The encoder adds the time for encoding the video signal and the time the compressed signal is in the output buffer to the total latency. Delta T network is the time needed to transmit the compressed data over the network. The decoder adds latency through the input buffer of the compressed data as well as through the actual decoding. Finally, the latency of the output device is added to the total latency, typically a display. Besides the network delay, the major delay results from the codec and its corresponding buffers. Whereas the buffer size is mostly dependent on the mode, either constant bitrate mode or variable bitrate mode, and the compression method used, the delay resulting from the coding is defined by the architecture. To meet the above requirements, we have developed a low latency video coding. Firstly, I will talk about the encoder. Our H.264 AVC baseline profile compliant video encoder is designed around a 5-stage macroblock pipeline, as shown in the figure, to encode the incoming video data with a near constant bitrate in real time for formats up to level 4.1, which is an HD image. In stage 1, the video input interface converts the incoming stream data into a macroblock format. This way, the memory bandwidth can be used efficiently. After the image data and quantization parameter have been adjusted according to the set region of interest, the macroblocks are distributed to the intra and the inter pipeline. In the inter pipeline, the inter motion estimation is first performed with pixel accuracy, then the fractional motion estimation with subpixel accuracy using a search window of plus minus 13 pixels. Within the search window, the motion vectors are unrestricted. Finally, in stage 4, the chroma motion estimation together with the mode decision and the motion vector prediction is performed. In contrast, the parallel inter-pipeline in the first 2 stages are only used for delay. The intra-decoder in stage 4 does the intra-prediction and transforms the video macroblock by macroblock. On macroblock basis, either the residual data of the inter or the inter-pipeline are taken as basis for generating a baseline compliant video bitstream using a context adaptive variable length coding entropy decoder encoder in the stage 5. At this point, the bitrate is very variable. After stage 5, the rate control block ensures a constant target bitrate. To avoid exceeding the bandwidth of the wireless link under any circumstances, we combined 3 approaches for the rate control. In general, the optimization strategy should work in such a way that the produced bitrate fits the target bitrate as well as possible, and on the other hand, the best image quality is achieved at this bitrate. The first approach is to adjust the QP at the macroblock level. Obtain the target bitrate as well as possible. Choose the QP as low as possible to achieve the best quality. And try to minimize the variations of QP within one frame and from frame to frame whenever possible, because the subjective quality would suffer from many QP changes. The second approach is a following bitstream buffer to smooth the resulting variable bitrate. The buffer is written with a variable bitrate and continuously read out. With a large buffer, more variation can be smoothed out, resulting in small QP changes. However, this would increase the latency. Since the rate control is not in all cases able to hit the target bitrate, variations are allowed to a certain over a limit. This means that we have combined constant bitrate and variable bitrate to a capped variable bitrate control strategy. As a third approach, we use IM. We use IM frames. We not use IM frames, we only use P frames. Because normally a video consists of a sequence of I and P frames, where I frames and especially IDF frames serve as the synchronization point for the decoder. The periodic I frames would result in high data rate peaks or in quality degradation. To avoid this, we are using only P frames with embedded I macroblock stripes, except for the very first I image, as shown in the figure. This complete intra update is done. The complete intra update is done over several successive P frames, as the figure shows. This results in an almost uniform distribution of the inter-block specific data rate over a group of pictures, which is ideal for wireless links, because the data rate is more uniform. Our goal is to ensure a high image quality in interesting image regions, even when transmitting via a low bandwidth data link. For this purpose, regions of interest can be set dynamically. Within the region of interest, the macroblocks are encoded with a lower QP, which results in a higher image quality. All macroblocks outside the region of interest are encoded with a QP difference higher QP. This results in a lower bitrate due to the lower image quality. The lower bitrate of the current frame leads in the rate control to the use of a lower QP for the next frame. This causes the data rate to approach the target bitrate again after a few frames. But more bits are used for encoding the region of interest than for the environment. Here a short example of the influence of region of interest. The image quality within the region of interest within the grid box is much better, as you can see on the levers. And now I would like to show you a short video example. I hope it works. It does not work. Now. As you can see, we have here 3 regions of interest defined. And the rest of the image is, there we encode only the luminance channel to reduce the bitrate even further. One region of interest is also only encoded with a luminance channel. And as you can see, the image quality within these boxes, these green boxes, is much better than outside these boxes, because we encoded more bits within the region of interest. Okay, then I will switch back to the presentation. And to the time constraints, we cannot present our decoder, but you can find more information about this in our paper. And now I want to calculate the latency for the overall system of encoder and decoder. For the video stream, we assume an HD stream at 25 frames per second and a clock of 160 megahertz for encoder and decoder. To achieve a minimal latency, we want to buffer only one macroblock row. For the calculation, we use the formula presented above. The latency of the video source depends on it and is unknown. The double buffer at the encoder input stores one macroblock line and therefore adds 120 macroblock latency. Each of the 5 encoder stages of the macroblock pipeline is adding another macroblock latency. As a result, delta T encode is 0.47 milliseconds. The output buffer, which stores one macroblock line, adds 0.59 milliseconds latency. Delta T network is unknown and may vary significantly depending on the used network. The input buffer of the decoder has the same size as the output buffer of the encoder, 0.59 milliseconds. The 3 decoder stages mean 3 macroblock delay, so that delta T decode is 0.012 milliseconds. Delta T video output is also unknown because it depends on the display. The total latency of the system is thus 1.662 milliseconds plus the unknown latencies. With these latency values, it is quite possible to get below 40 milliseconds total latency, which corresponds to a response within 1 frame and 25 frames per second. Now let's take a look at the Pearson-R curves of our hardware encoder. We encoded 3 different sequences with different target bitrates as shown in the figure. As the target bitrate increases, the quality of the encoded video also increases. Despite the same bitrate, the 3 sequences have a very different quality. Thus, it becomes clear that the data rate depends strongly on the sequence content. A sequence with high motion like CrowdRAM achieves a significantly lower Pearson-R at similar bitrate compared to a sequence with little motion like Sunflower, which is at the top, as you can see. Now we are looking at the influence of 4 regions of interest, each with 224 pixels times 224 on the image quality in this sequence with the lowest quality, which is CrowdRAM. In this sequence, 10% of the macroblocks are regions of interest. The Pearson-R curve in the middle shows a coding without regions of interest as reference. The upper curve shows the Pearson-R only for the region of interest, and the lower curve for the complete image, including the region of interest. Our region of interest mechanism allows us to achieve a significantly higher quality, around 9 dB better, within these areas compared to a sequence without region of interest. But since the data rate is constant, this is achieved at the expense of the quality of the rest of the image. There, the Pearson-R is about 3 dB lower than without region of interest, because we are using a lower bit rate outside the region of interest. Finally, our conclusion and future work. We have developed an architecture of a low complexity H.264 video codec, which has been optimized regarding its usage in technical image processing applications. It supports regions of interest, rate control, and still has a moderate coding efficiency. The architecture meets all requirements of the planned C rescue system and can even be used on low-end FPGAs due to its low complexity. As further works, we want to extend the system with a DCNN, which will be trained to detect shipwrecked people. In addition, We want to integrate the low latency encoding concept into our HEVC encoder to improve coding efficiency. Yeah, this was my presentation. Thank you very much for listening. And do you have any questions?
Thank you. We have time for 1 or 2 short questions.
Actually, I have a question.
Yeah.
Maybe I missed it, but the application was to detect people or objects of interest inside water, right? For
Yes.
Rescuing. Is it then also necessary to actually send the rest of the data? I mean, if you have the regions of interest and the rest is, if you know that it's water, wouldn't it save on bandwidth if you just don't send that data? Or maybe you are not sending it, and I miss it.
And actually, we want to send it because it's possible that region of interest detection machine learning algorithm in the UOV does not detect all region of interest correctly, because it's quite a low complexity machine learning algorithm, because the requirements or the restrictions within the UOV, because we have not much power, and yeah. And then it would be better to transmit all the image, and then yeah, you can detect manually some missed region of interest.
Okay, but of course, then you do risk the receive when you receive it, because you are encoding it with a lower quality. You have to. That's the balance, right? That you make.
Yes.
Because if you miss something, you need a better. The ground station needs to have a better classification to detect a region of interest that might have been missed, even though then the image quality is lower.
Yes, but at the ground station we have a lot of more power available, so it would be possible.
Okay. Thank you.
You're welcome.
I have a question in the same way. I just understand why you try to work on video with the latency problem. If the focus, the goal of the application is to detect something that normally don't move in the image, so ship for boats perhaps, but if you want to identify person, it's not be more easy to work on in a single image, and after, if need, by the ground station decision, take other images to have a more better classification or results.
I'm not sure if I understand this question correctly.
You work on video sequence. You
Yes.
work to ensure the latency, that because you work on video sequences, but you need to identify a person in the scene, and the person in the scene normally don't move very fast. So yes. you have a latency that why you don't try to also to think to work on the single image without the content of the latency.
Because the drone is moving, and sometimes it's better to have the information of the video to detect the person in the water correctly, because we have some information about this moving pictures.
Okay, but just because you think that after you need to control the movement of like a vehicle, like a cars, but the drone need to be remoted, controlled to move and keep different part of the sea. There is also this is in mind.
Yes.
Okay.
Okay, I think we can then return back to this issue later, just to keep the time. Sorry,
okay.
I didn't choose the role to be the timekeeper, but but it turned out like this. So thank you once more, and I would like to invite the next speaker, so you can turn off sharing your screen.
Okay.
And Naouel,
Hello?
I don't, yes,
Can you hear
you
me?
can try to, yes, we can hear you. Now you can start sharing, and I will just shortly introduce you. Naouel Haggui was born, sorry if I pronounce it not correctly, in Kasser in Tunisia. She received the electrical engineering degree from the National Engineering School of Sfax in Tunisia in 2019. And since 2020, she has joined the Electronics and Information Technology Laboratory in Sfax and jointly the Institute of Electronics and Telecommunications of Rennes, where she is currently a PhD student, and her research interests include video coding, data flow modelization, and hardware implementation using embedded multi-core platforms. The Zoom platform is yours.
Hi, everyone. First of all, I'd love to thank you all for being here today. My name is Naouel Haggui. Today I'm going to present my work entitled Multiple Transform Selection Concept Modeling and Implementation using Interface-Based SDF Graph. Through this presentation, Through this presentation, we are going to start with an introduction. Then we will move on to the multiple transform selection concept, talking about some definition and feature. Then we will move on to the proposed model, present its experimental result, and finally, of course, some conclusion and perspective. Video are taken all over the world. It's projected to account 82% of global internet traffic by 2022. Actually, we can all notice the huge use of video websites like YouTube, Netflix, the huge use of gaming platform, especially in 2020 and this year. Obviously, it's going to increase due to COVID-19, which forced us to stay at home, unfortunately, and we use remote working. Through years, multiple video coding video formats appeared, so that multiple new video coding standards showed up, like AVC that targets HD resolution, HEVC that target 4K and Ultra HD resolution, and finally versatile video coding, which just has been released, and it could target 8K resolution. Compared to HEVC, VVC enable 40% of coding gain for the same visual quality, and this is the standard that we are going to work with. As you can see here, a video coding process is composing from multiple units. In this work, we will focus on the transform unit, more specifically on the multiple transform selection concept. What is it? Well, multiple transform selection concept has been introduced in VVC. It enabled the VVC encoder to select the transform that minimize the rate distortion between the predefined trigonometric transformation, including the well-known discrete cosinus transform type 8 and type 2, DCT8 and DCT2, and the discrete sines transform DST7. For the principle, as you can see here, if the DST7 is chosen for the first direction, VVC enable the use of DST7 or DCT8 for the second direction. The same for DCT8, unlike DCT2, the block in yellow, it is applied for both directions once it is selected. Also, MTS has three main features. The first one is the butterfly decomposition for DCT2. As you can see here, you can notice from this equation that the ones for DCT2 is different because the transform size n is linear in this equation, which enable the recursive detection of larger block size from smaller one, thus the butterfly decomposition. Another important feature, which is the DCT8 can be deduced from DST7 based on this equation. The third and final feature is the zeroing. In order to reduce the computational complexity of the multiple transform selection concept, high frequency coefficient are zeroed out for larger block size, We mean by larger block size, the block of size 64 for DCT2 and order 32 for DCT8 and DST7. Now let's move on to the MTS data flow model. But before we getting into the detail, let's discover what stands behind this model or implementation. In order to reduce the complexity of the MTS concept, multiple optimization has been proposed, once by reducing the number of addition and multiplication, or by reducing one transform type from another, and other multiple proposition. In this work, we are going to propose a new optimization, new software optimization for the multiple transform selection concept based on data flow modeling, which is a network of computing unit actor exchanging token through unidirectional buffered links FIFO. Now, if you ask me why data flow, I will tell you because data flow is useful for capturing important data dependency, exploring parallelism between system cores, and the most important, that with the same data flow model, we could target several hardware, such as FPGA, CAL array, x86, multi-DSP, etc. In order to realize the MTS model, we use Prism, which is an open source rapid prototyping tool that generates code for heterogeneous multi-core embedded system. In order to create this multi-core algorithm, we need to realize some tasks first, which are the algorithm graph, the SDF, the architecture graph, the scenario, and the workflow. The algorithm graph used in Prism is a statistic specialization of the PSDF graph called Interface Based SDF graph, EBSDF. The EBSDF graph aims at present a full and clear description of the process and the data flowing between actors. As you can see here, we managed to realize two EBSDF graphs that we will discuss in the coming slides. The kind of architecture graph used in Prism is called system level architecture graph. It is a set of core that related to a shared memory in order to communicate. As you can see here, those are some examples. This one with the use of one single core, two cores, 3 and 4, and we could use as many as we want. Now let's move on to the scenario, which is the most important part as it contains all the parameters that controls the application performance, such as the EBSDF graph to be used, the architecture graph to be used, and the execution time of each actor. Actually, the scheduling algorithm in Prism by default assume that all the actor has the same execution time equal to 100 time units. This and a current knowledge of the execution time of each actor could result in bad decision by the scheduler, so that a bad impact on the application performance. So that each time we made a modification in the EBSDF graph, we remeasure the execution time of each graph and update the scenario with the new measure of the execution time. Prism contains multiple tasks in order to generate the code. Display the Gantt chart. As you can see here, it's a description of the partitioning of tasks according to the number of used core. It also contains some optimization tasks like the software pipelining, which breaks the critical path into shorter one by introducing delays, which relaxes the dependency between actors and make possible the concurrent execution of different parts of the critical path. Also, another one is the memory optimization, Both of those tasks serves at reducing the execution time so that speed up the application, which is our goal. Now, after doing all of those, let's move on to the result and interpretation. The first model, as you can see, is based on this EP-SDF graph. If you focus on it, you will realize that the transform actor is different, well, because it is an hierarchical actor, which means that if we get inside it, we will realize that there is there is a multiple actor in the inside. This fact reduces the execution time of each actor, so that a fine-grained data flow model. This fine-grained data flow model resulted in an execution time on one core too short compared to the one on 2, 3, and 4 core, as the curve in blue shows. Shocking, right? Parallelism is supposed to reduce the execution time while increasing the core number, like the theoretical result showed the curve on red. And our experimental result shows just the opposite. So this could be explained by several reasons, which are that fine-grained granularity makes every process, even those characterized with a very, very short execution time, with a great importance and with a great bad impact in the application performance. All the process actually that the operating system performs, such as allowing the application to create threads, let them communicate, synchronize tasks, providing time, memory, and preferred management tool, are considered in this model. In this kind of models, synchronization turns to be very, very costly. So, in a nutshell, to achieve efficient performance, task management and data transfer time should not be too long with respect to the computing times. Now, let's move on. However, this model could yield in a good result if with a high speed up, if we send several blocks to be transformed at the same time. As this figure shows, when increasing the number of blocks to be transformed, we are getting closer and closer to the theoretical result, which is the curve on green. Now let's move on to the second model, which has a simpler EP-SDF graph. It is composed of two low-level, non-hierarchical actors, thus a coarse-grained data flow model. The fundamental idea behind the second implementation is the exploration of the independency between the blocks to be transformed in order to get parallelism. This table, as you can see, presents the speed up and execution time according to the core number. While processing two blocks, as you can notice here, the execution time is decreasing when passing from one single core to two cores. Thus, a speed up equal to 1.872, which is near to the theoretical result, which is 2 while using 2 cores. This second table is another example that proves the efficiency of the coarse-grained data flow model on the x86 architecture. For both of those figures, the blue wave introduced the theoretical case, whereas the red wave introduced the result, the experimental result of applying the MTS concept respectively on 8 and 1000 blocks. The first figure illustrates the speed up of the MTS concept on a 4-core machine. However, the second one on 24 core machine, for both the simulation, the experimental results show a speed up nears to the theoretical result, which is good. And that's proof also the efficiency of the second model, the coarse grain model on x86 architecture. Therefore, the benefits of using data flow modeling on the MTS concept. As a conclusion, the MTS concept has proven the implementation of the MTS concept using Prism has evidenced its efficiency while using a coarse grain data flow model on x86 architecture. Actually, in order to create an efficient solution for x86 architecture, each actor must perform a significant number of calculations, high or medium granularity. It is important to choose the level of granularity to be used according to the target architecture before modeling an application. And as perspective, we aim on future to use Prism to implement and to model other unit of video coding, such as a complete decoder or encoder maybe. And we aim at studying the fine-grained granularity effect on CalRay, multi-DSP, and FPGA architecture. Thank you for your attention.
Thank you very much. Maybe one question, if somebody has.
I cannot see any question in the. Can everybody hear me?
Yes, yes. I think maybe there are no questions at this point.
Thank you, then.
So thank you once more. And the next speaker will be Krzysztof Blachut. So could you please, okay.
Yes, hello.
Hello.
Can you hear me?
So,
okay.
Yes, I can hear you. So actually Krzysztof is from my research team in Krakow here. He's a PhD student at AGH University of Science and Technology. He is the member of our laboratory and his scientific interests include embedded vision, especially FPGAs in autonomous vehicles and video surveillance systems. And he will present our work about automotive perception system evaluation with reference data obtained by a UAV. This is a joint collaboration between our group and our colleagues from the Aptiv company, which office has an R&D office in Krakow. So the floor is yours.
Okay, so thank you for the introduction. I will present automotive perception system evaluation with reference data obtained by a UAV. At first, as you know, there are many different automotive perception systems, including cameras, typical RGB, infrared, stereo ones. There are LiDARs, radars, GPS systems, but also ultrasonic and inertial sensors used in automotive industry. So why the problem of the evaluation is so important? Well, in terms of advanced driver assistance systems, it is quite a relatively easy task. For example, for adaptive cruise control or lane departure warning and so on. However, in autonomous driving for autonomous vehicles, it is more complicated task. There are several reasons. At first, of course, there is a required very high level of safety. There are used multiple sensors in these vehicles. To really test and evaluate them, there is a need to make a lot of diverse and complex test scenarios where there are different types of objects, just like cars, bikes, pedestrians, obstacles, etc. One of the problems is that, especially during dynamic experiments, there is no precise information about position of all the objects. So how can we test the accuracy of these sensors? There are some existing solutions that use additional precise ones, but they require usually manual labeling, which is very time and work consuming. For example, they use precise GPS system, but there are several problems. For example, there is a limited number of objects. It is quite an expensive system, and the frame rate is not very high. Another problem is that the GPS signal is not available everywhere, and we receive the global position instead of local around the tested vehicles, which is what we are really interested in. There are maybe some occlusions when the reference sensors are placed on the tested vehicles, so they have the same perspective as the tested ones. And some expensive integrated systems, there may be necessary. There are some expensive integrated systems, but yeah, the cost is very high, so that's a problem. So our solution is to use a UAV, also known as drone, that is hovering above the test vehicle. The drone should be equipped with a high-quality camera, so then we can use computer vision methods to detect and localize the objects that we are interested in. On the picture, you can see the vehicle setup that we used in our experiment. It is equipped with Aruco marker and LED system, which I will talk later about. There is also a Hesai Panda lidar and differential GPS system. Both of them work at a frequency of 10 Hz. And for the data acquisition, we used a computer with a robot operating system. In case of the drone, we used the commercial DJI Mavic Air equipped with a 4K camera. In the target solution, we would like to use the data from drone's camera as a reference, as a ground truth. But in this work, we wanted to compare the data, the measurements from the UAV's camera and the precise differential GPS that we used as a ground truth. We compared two vision-based methods based on Aruco markers and deep convolutional neural network. We also did some initial evaluation of the sensor, and we chose the lidar. When using different types of sensors, usually there is a need to synchronize them. We decided to use a vision-based approach based on 8 LED system, which was connected to Raspberry Pi. It was placed on the host vehicle in a known position with regard to the Aruco marker. And the source of the synchronization signal were the messages from the lidar system. Why have we decided to use such a solution? Well, mainly because we were using off-the-shelf UAV, and the evaluated lidar was working at pretty low frequencies, so the very precise synchronization wasn't necessary at this point. In case of Aruco detection, we used the codes that you can see on the picture. We used them for the vehicle detection. We printed them on a foil and placed on the roofs of vehicles. This kind of markers are pretty robust to illumination changes and changing weather, which is very important for evaluation of subsystems. There are many unique identifiers, so there are many multiple codes, so we can easily distinguish different types of objects using them. And as we printed them, we had known dimensions in reality, so it was later possible to convert the distances from pixels to the metric unit. For detection of these markers, we used standard OpenCV functions. The results that we got were the distances of these markers with regard to the camera, which roughly corresponds to the distance from the vehicles to the camera. And we also calculated the bounding boxes for all the vehicles. For the host car, as I mentioned earlier, we had to also detect the LEDs. As I said, they were placed in predetermined position, so their detection was pretty easy. And then we used the picture in grayscale to see if a particular diode is on or it is off. We selected a threshold value in that grayscale. Of course, it can be adjusted according to the weather. Sometimes it is more sunny or more cloudy, so the threshold may be slightly higher or lower. And to make it more robust, we used a small neighborhood of a single LED. As you can see on the picture, the green circles are the diodes that are on, and the red ones are off. Finally, we calculated the distances between the host car and other vehicles. We used for this simple Euclidean norm. As you can see on the picture, we calculated two distances for each vehicle. First one was from the host's ARUCO marker to the ARUCO of the other vehicle. And the second distance was from the same point to the bounding box of the vehicle. Of course, it's worth mentioning that in case of wrong marker center detection, we got some inaccuracies in calculated distances. The second method that we wanted to check was based on a DCNN. We used a mask RCNN detector, which was based on convolutional network ResNet architecture. Why have we decided to use such a network? Well, it usually gives very precise segmentation of objects, which was crucial in our experiment. The network was trained on the COCO 2017 set, but there were some problems with detections from the drone's perspective. So we decided to use another benchmark to train it further. In that benchmark were objects from the drone's perspective, so that was what we really needed. And as expected, after training, we got some better results and the detections were more correct. Finally, we calculated distances from the host's centroid to segmented masks of other vehicles. Host car's centroid roughly corresponds to the center of the ARUCO marker. On the sequence, we used tracking by detection system. However, there were some problems with additional detections where the network was treated the car with its shadow as another object than a vehicle without its shadow. Here you can see a sample result of our experiment with DCNN. And we decided to make two scenarios. The first one was a static one, where all vehicles remained stationary. We placed them in predetermined positions. The UAV was hovering over that scene at 35 meters. In case of higher altitude, we had a wider scene, which was good, but there were some problems with detections, for example, with the LEDs, because they were not visible. And they calculated inaccuracy of distances, and the distances calculated were more inaccurate. As I said earlier, as a ground truth, we used a precise differential GPS. And LiDAR and vision data we just recorded and processed them offline. Here you can see the orthophoto map of the static experiment and the corresponding LiDAR point cloud. Okay, so we measured these distances using different methods, our ground truth GPS, and then two vision methods, ARUCO DCNN, and a LiDAR. As you can see in the last three columns, the differences for different vehicles were mostly below half of the meter with regard to the ground truth. So I think it was pretty good, especially if you see that the distances were over 20 meters. So then we decided to make a dynamic experiment where the host car was driving between the static vehicles. At the same time, the drone was flying above the moving car at an altitude of around 25 meters. We calculated only distances to the bounding boxes of the tested vehicles. As you can see in the table, the results in this experiment were not as good as in the static one. For example, for AeroCord and DCNN, they were over 1 meter higher or lower than the GPS system. So yes, this experiment was more challenging. Here you can see some sample screens from the CNN results on the sequence. So what are the possible sources of errors with regard to the GPS, our ground truth? At first, the AeroCo markers, probably the position and size of the detected markers. In case they were not detected correctly, we had some wrong positions and also wrong scaling from pixels to the metric unit. Some kind of problems during the dynamic experiment caused the shadows cast by LEDs on the AeroCo marker. So yeah, it caused some additional detection problems. In case of DCNN method, the source of errors was sometimes the segmentation of the objects, because it wasn't always very precise. And also, as in the other vision methods, scaling to the metric unit from the pixels. And as I mentioned earlier, problematic were the car shadows, where they were sometimes treated as the other object. In case of a LiDAR sensor, the problematic was the lower density of points for the farther objects, and of course manual labeling, which sometimes it is prone to the human errors. Anyway, the errors on the dynamic experiment were lower than for the vision methods, and we get a wider scene. So that means it is quite a challenging task to evaluate such a sensor. The last source of problems probably was a common coordinate system. We chose it at the LiDAR one. There was a need to express all the measurements in one system to compare them. Possible solution for the vision method, maybe, for example, combined method to use the advantages of both AeroCo and DCNN. Okay, so we did some simple evaluation of vehicle perception system. We proposed here a concept of using the drone with an ultra high definition camera. As a test case, we choose vehicle detection with the LiDAR sensor, which was an evaluated one. For the static experiment, the results were pretty good because the errors with regard to the ground truth were mostly below half of the meter. However, for the dynamic tests, the errors were much higher because they were up to 1.5 meter. So surely there is a need to improvement for the vision algorithms, especially in case of problematic shadows detections and to enable higher altitude detections. The aim of the future work is surely a fully automatic solution. To make it possible, we will have to use a custom-built drone that would enable a wireless frame synchronization instead of using the LED system. It would be good to do some onboard processing, probably using system on chip or embedded GPU device. And we would like the drone to track and follow the moving host vehicle. As I said earlier, the vision algorithm needs some refinement for vehicles, maybe a combined method, and we would like to detect other objects, probably because, using DCNN. And of course, there are required multiple tests in various conditions to check our solution. Thank you for your attention.
Thank you very much. Are there some questions? I see everybody is very shy. But I'm not the right person to ask question to this paper. I can try to another one. So anyway, if you come up with a question, then we can return back to it in the afternoon session. Oh, Andrea.
Yes, I think that it's a good idea. We have a time after also to open discussion. Okay. Perhaps there is a different presentation that share a different point that could be discussed after. In any case.
Okay. Okay. So now we have a 10 minutes virtual coffee break, or I hope for some of you a real coffee break. So get some refreshment, and we will start at 12 o'clock with the presentation of Oğuz. So see you in 10 minutes. Hello again. So now we would like to ask Oğuz to present the screen. Okay.
Let's see. Stop. All right. I hope it's visible and that everyone can hear me.
Not here, yes. Visible now, yes. Okay, so I will just shortly introduce. Oğuz is a PhD student at the University of Twente, and he's doing research on low power embedded systems and ASIC design, and he mostly focuses on automotive applications and radar. So the Zoom platform is yours.
All right, thank you. Hello, everyone. I'm Oğuz, and as Thomas said, yes, I am a PhD student. Marco Bakoy is my supervisor. He's a part-time professor at our group. He also works at NXP. My presentation is about low-power sign magnitude FFT design for FMCW radar signal processing, which is a whole mouthful and which I'm going to explain in this presentation. Okay, first of all, let me give you an overview. I'm going to talk a little bit about the context in which we did our research, the problems that we have, and the goals that we tried to achieve. I'm going to talk a little bit about the basic principles of FMCW radar, some of the properties of the fast Fourier transform that we exploit. And I'm going to show you our proposed design, some power results, and then I'm going to conclude this presentation and you can ask questions. Okay, so first of all, the context is as follows. Several companies have started making fully integrated FMCW radar chips that combine the analog front end for the radar antennas and the digital signal processing in a single chip. These can be used, for example, in cars and other automobiles as cheap sensors for distance, speed, and angle measurements. However, as Diana this morning in her presentation also showed, one of the issues is that power is an issue, not only because of let's say a car battery, but also power usage causes heat dissipation issues. These chips that exist usually power throttle because they use too much power because of a lot of processing that they have to do. Automotive packaging is rated up to 2 watts, so ideally we would want to stay under that. The analog front end roughly uses half the power and the digital part uses the other half, where the signal processing part is a majority of it. So we want to use lower power. So first of all, FMCW radar, or frequency modulated continuous wave radar, works by transmitting a chirp signal. This is a signal that increases in frequency over time. Compared to a normal radar, where you use the time difference between transmission and reception, with FMCW radar, you can also use the delta frequency to determine the distance of an object to the radar. So how do we get this delta frequency? simply by demodulating, and we do that by mixing the received and the transmitted signal. This gives us a beat signal. And a beat signal is a summation of sinusoidal signals of these delta frequencies, and it's one per reflection. So how do we then get these sinusoidal? In this case, the fast Fourier transform. Here we have a signal that consists of two sine waves as an example. After applying the fast Fourier transform, we have on the right, we see two peaks which correspond to the two sine waves. The higher the frequency, the farther away an object is. So to put everything in one image, if we take the Fourier transform of these overlapping parts, what we get is the range, which are these columns in the lower left. If we do this multiple times and we paste these, we'll put these ranges next to each other and then take the Fourier transform of all the rows, then we get what is called a range velocity map or range Doppler map. So we now not only know the distance of an object, but also its relative velocity. So this is an example of that. Here we have mostly the green and bluish color that you see is mostly noise. And this yellow peak that we have here surrounded by a red box is an object that has been detected. Now, here's a small overview of the fast Fourier transform. On the left, you see the butterfly unit, which is the basic unit of the FFT. I'm going to talk a little bit more about that later. On the right, you see how you can have multiple of these simple blocks on the left, combine them to do perform the FFT on more samples, on larger samples. So one of the things that I want to note is that due to physics, the power of the received signal is often way less, way smaller than the power of the transmitted signal. Therefore, we have to deal with mostly very small values, usually that lie underneath the noise floor of our ADCs. So how do we then extract this, even though it's below the noise floor? Well, the Fourier transform has this interesting property called the processing gain. So what happens is, if you take n samples and perform the FFT on it, the correlated signals, so the sinusoidal signals inside that, will actually grow n times at the end of the Fourier transform. However, noise only will grow by square root of n. So if you just take enough samples, you can extract signals that are far below your noise floor. But of course, this requires that you do a lot of processing, which is why these chips usually consume a lot of power. And this is what we try to avoid. So here I have given an example of performing the FFT on 1024 samples of a single sine wave. And this is done in 10 stages. We can see that very quickly throughout the stages, the intermediate values are becoming more and more sparse. Actually, sparse is not the right word because that would imply that all the values are zero except for the peaks, but it's mostly noise and we have very few peaks. And we will exploit this in a little bit. So to return back to the butterfly unit of the FFT, we've implemented this, and when we processed actual radar data, we found that the 4 multipliers here on the lower left consume by far the most amount of power. So this is what we try to optimize first. And we found out that it's due to the number format that we chose. So normally, 2's complement numbers are used for signed integers because they're very ubiquitous. The device you're viewing this on right now most likely uses 2's complement for signed arithmetic. This is done because adding and subtraction can be done with the same hardware. It's very easy to implement. And but in terms of power, there's one problem. When you switch a sign of a value, you have to invert all bits and then add a 1, which is called the 2's complement operation. So you can see here as an example, when you go from 1 to -1 or back, almost all the bits are flipping. This means that we have a high switching activity, and that causes a lot of dynamic power usage. So we thought, why not use something else? And we looked at signed magnitude. As the name implies, it consists of just a sign bit and the magnitude bits. In this case, the most significant bit is used as the sign, and the rest is just a positive value because by definition, the magnitude is positive. As you can see, if you switch from -1 to 1, you only are flipping 1 bit, and therefore you have very low switching activity. Now, why is this not used more often in arithmetic? The problem is that adding numbers with different signs is a bit difficult, because you can see if you, on the left with 2's complement, if you add 1 and -1, you would actually get 0. But if you would add -1 and 1 in sign magnitude, you would get -2, which is of course wrong. To deal with that, you have to convert negative numbers into 2's complement negative numbers, perform the operation, and then convert back to sign magnitude, which means you have conversion overhead. But this is for addition. With multiplication, you don't have this problem because you only have to multiply the magnitudes. So therefore we came up with this hardware design. It's the same butterfly unit, but now the inputs on the left are in sign magnitude format. We perform unsigned multiplication. And after that, we have these blocks with a C inside. They are converter blocks. They convert negative numbers from sign magnitude back into 2's complement. The subtraction, addition, and rounding is then done in 2's complement. And then additionally, conditionally, they're converted back into sign magnitude. In the image I showed you before with the butterfly-looking structure, you saw that if the output of this butterfly unit in the next stage, if it's going to be processed by the multipliers, then we want to convert back to sign magnitude, or else we keep it 2's complement in order to avoid unnecessary conversions. So the problem is this actually did not lower the power usage at all. And that's because we use the Booth multiplier. The Booth multiplier isn't a very often used type of multiplier because it's very fast. And this is because it generates half the partial products of, for example, an array multiplier. However, in terms of power, the problem is that even if you give it just positive numbers, it can still generate negative numbers inside. So here's an example. If we perform 1 times 3, a Booth multiplier would calculate that as -1 times 1 plus 4 times 1, which is 3, it's correct. But the first partial product, as you can see, it's colored in dark gray, generates -1. So all the bits are flipping. And this has to ripple throughout the entire multiplier, and that causes, again, high power usage, high dynamic power usage. So therefore, we propose an unsigned Booth multiplier. I found exactly one other paper that has unsigned Booth multiplier in the title, but they use the normal Booth multiplier with positive numbers, so I don't know exactly what they're trying to do. So this is an actual unsigned Booth multiplier. It only generates positive partial products, so we can never have this negative numbers inside them. So in this case, the implementation is very simple. If you take an A times B multiplier, for each consecutive pair of consecutive bits of B, so bit B0 and B1, B2 and B3, B4 and B5, and so on, you drive a multiplexer that multiplexes 4 values, either 0 times A, just of course 0, 1 times A, 2 times A, or 3 times A. But here you have a problem because 3 times A is not easy to generate. So you would either have to pre-compute that before it enters the multiplier, but then that would lie in your critical path, making the entire multiplier much slower. Different way, where apparently I have independently rediscovered the redundant binary multipliers, because what you do is you generate 2 partial products. One generates either 0, 1, or 2 times A, and the other one generates either 0 or 1 times A. That's the bit on the right here. If you want to generate 3 times A, the bit on the left will generate 2 times A, and the one on the right generates 1 times A. You can add these 2 together. The problem here is now you have twice as many partial products, which is the whole point of the Booth multiplier, is to lower the amount of partial products to become faster. But we use a Wallace tree, which is used very often, to add these partial products together. And the depth, if you have, for 32-bit multiplier, which we use, you have 16 partial products normally, your depth of your Wallace tree would be 6 full adders, but if you use 32 partial products, or 31 in our case, you have 8 full adders. Now, yes, this is a little bit of overhead, but it is still much faster than first pre-computing 3 times A and then using the previous design that I showed here. So here's are the synthesis results first. We used TSMC's 40 nanometer standard cells and implemented both designs. So the reference two's complement design is blue and our proposed design is in green. First of all, we can see that the maximum frequency is a little bit lower, about 6.7%. This is because the multiplier is a little bit slower and we have the conversion to and from two's complement. So the area of our design is almost 50% bigger at the maximum frequency. Now, of course, this is because we generate twice as many partial products and we have 4 multipliers, of course. But at maximum frequency, the power usage and area grows exponentially. So if we take a look at a more reasonable 500 megahertz, then our design is only up to almost 36% larger. Normally, this is not really a problem in these kinds of chips because the analog front end is so large compared to the digital signal processing part that even if this was 10 times larger than what we have now, it still is very small. So it doesn't really matter that much, but it's still, I wanted to show it here just as a comparison. If we take a look at the power usage, the interesting thing is that we performed the Fourier transforms, the FFTs on a full radar frame. And we did 2 passes. One is the range pass, this the columns that I showed you before, and then which is indicated by an R. And then we have the D, which is the Doppler, that's the performing the FFTs as rows. And we can see that we can save at 500 megahertz between 40 and 46% lower power for the entire design. That's quite significant for just changing the number format and even with the conversion overhead. So if we just take the same input and only look at the power results of just the multipliers themselves, we see that we can save between 59 and 66% power, which is very significant because now in our design, the dominating power is not the multipliers anymore, but it's now the adders. And just to show you that this is really because we are not switching all the higher bits because we use sign magnitude. Here we have simulated the designs as well, but now we use random data. So the point with the random data is the Fourier transform, because random data is uncorrelated data, it will actually smear the signal power out over all bins. What I showed you before is you had the 10 stages, and even though you have a large input, a large sine wave, very quickly that gets filtered and you only have one peak in the end and all the rest is just very small numbers or just noise. But random data gets smeared over all bits, so all of your internal values will be at least as big as your input because like I showed you before, the processing gain makes sure that all your signals are growing, except random data grows square root of n instead of n for signals. If we use 12 bits of random data, which is the blue and the orange one, with the orange being our design, we see that we save still for random data 42% power. But if we use the full 32 bits of random data, meaning that all butterfly units in every stage will process 32 bits of random data, then our design, which is the green one compared to the red one for two's complement, actually uses 19% more power compared to two's complement. And this really shows you that because we have so few bits, flipping of the upper bits, that's why we can save so much power. So to conclude, the sparsity inside our FFT stages allows us to exploit the primary advantage of sign magnitude, which is not to switch or very low switching activity. And therefore, we've proposed a hybrid FFT design, and with our proposed unsigned multiplier, and it uses much less power compared to just a straight up two's complement FFT implementation. And this is despite the conversion overhead. So we lose a little bit in speed, but we gain a lot in power efficiency. So that was my presentation. Thank you for your attention. Are there any questions?
Thank you very much. We have time for 1 or 2 questions. So again, maybe some questions will arise after lunch. So
Okay.
maybe, so thank you once more for the interesting presentation. And now we will move to the second presentation of this short session. So if Karol could, oh, okay. So I would like to introduce Karol Desnos. She's associate professor at INSA-REN, a French engineering school, and a researcher in the Institute of Electronic and Digital Technologies. And his research interests are design, automation, optimization of embedded systems for modern, heterogeneous, multi and many core targets. So let's present.
Okay, thank you. Can everyone hear me? Yes, I assume it's okay.
Yes.
Okay, great. So good morning, everyone. I'm Karol Desnos, and today I'm going to present you the work on JJ-LATI. And the title of the paper is a lightweight artificial intelligence through generic and evaluable program graph. And this work was realized in a collaboration between INSA and the IETR lab and the Silicon company in Rennes in France. So what are the 3 objectives of the paper? The first one is to introduce a new multipurpose reinforcement learning library, and I will explain that in detail. One of the key characteristics of this library that I want to present is also that it is an embeddable and deterministic parallelism parallel library. And finally, the third objective of the paper is to introduce the customizable aspect of this library. Unfortunately, due to time restrictions, I won't have enough time to present this customizability of the library, but I invite you to read the paper if you are interested in this third contribution of the paper. So, first of all, what is reinforcement library? In reinforcement library, you have an artificial intelligence called a learning agent that is interacting with a learning environment. And so by observing the state of the environment, the learning agent is able to react and to perform some actions on the environment, which will change the state of the environment. The state of the environment may also change because of time, because of randomness, or because of physical aspects. Then the state of the environment evolves, the learning agent has the ability to react again, and so on. For the learning agent to learn if it's doing something useful or not, we need to set up a third exchange of information between the learning environment and the learning agent, which is a reward. By giving a positive or a negative reward to the learning agent, the learning environment can help the learning agent learn something useful and to perform some useful action in the environment. So what are the technologies available for implementing such a learning agent? Nowadays, many people are using deep learning techniques or Q-learning technique to implement the reinforcement learning agent. What we are interested about in this paper is another technique for machine learning, which is tangled program graph. A tangled program graph, or TPG for short, is a reinforcement learning technique that was introduced in 2017 by Stephen Kelly and Malcolm Haywood from the University of Dalhousie in Canada. A TPG, so a tangled program graph, is the model that is used to power the reinforcement learning artificial intelligence. This graph is composed of teams, which are the vertices of the graph, actions, which are the leaves of the graphs, and programs, which are the edges of the graph. In order to understand how a TPG works, we must first present how the programs inside the TPGs work. So let's have a look at the program. If we consider the program as a black box, each program will receive a copy of the state of the environment. It will process it, and it will produce a number as a result. And you should not try to give any meaning to this number. It is just a number written by the program. What's inside the programs? Well, the programs can be understood as an assembly program, which is a set of instructions. The instructions will work directly on variables from the environment. So here, for example, you can use the value of some pixels of the environment as the operands of the instructions, but they can also work on the results of previous instructions. The result produced by the last instruction of the program will be considered as the result of the program. So these are the programs inside the TPG. So how does the TPG work? To understand that, let's focus on an example of an artificial intelligence that is learning how to play a video game. And so the actions of the graph, which are the leaves of the graph, if you don't remember, each of these actions is associated to a set of buttons of the controllers or of the video game, for example. So how does this work? First, we receive a new state of the environment, which is a set of pixels of the screen. Then we start from the root team, so the vertex of the graph with no incoming edge. We start from this root team and we execute all the programs on the outgoing edges of this root team. Each one of the program will return a value, and then we simply select the highest value, which is called a bid, and we go along this path. We go to a new team, and once again, we execute all the programs of the outgoing vertices of the outgoing edges of this team. We select the highest value, and eventually we reach an action. We perform this action on the environment. The state of the environment will change, and then we restart the process again from the root team of the Tangle program graph. And this is how you execute a Tangle program graph. So we have seen how to execute a TPG, but how do we train them? We train them using a genetic learning algorithm. In a genetic learning algorithm, you start from a population of learning agents which have poor capabilities. And if you take back the video game example, they will have a very low score. And then through a genetic evolution process, and by selecting the most fitted element of your population at each generation, eventually you want to reach a population, a final population, where the score of the populations are very high by natural selection process, Darwinism at its best. So how does this apply to the TPG? Well, when you are training a TPG, instead of a single root team, you have several root teams. And if you execute the TPG from each one of these root teams, you will have a different behavior. And so you will have a different score. So what you do is you evaluate the score that you get from each one of these root teams. You get a score for each root team. And these are the scores that you get for generation N. When you want to prepare the next generation of the genetic evolution process, you just discard the worst performing team. And you just kill them, you just remove them from your TPG. Then to repopulate your graph, you will randomly select some remaining vertices of the graph and copy them. In order not to have the same behavior as the one you just copied, you will then alter this new root team by performing some mutations on some of their programs. And so you change the target of their programs, or you change the set of instructions of the programs themselves. And by doing that, you create new root team for your graph, and by evaluating them again, you go to the next generation of the genetic evolution process. So TPGs are great, of course, otherwise I would not be presenting them. TPGs have proven to be very efficient learners. They have an adaptive complexity, which means that the topology of the graph adapts itself to the problem in which they are trained, contrary to deep Q-learning techniques, which have a fixed complexity set by the designer of the deep Q-learning algorithm. They are very fast. For the video game example, for Atari video games, they were able to perform 2 to 3 orders of magnitude faster than deep Q-learning framework with the same performance. And finally, they are very lightweight. The storage capacity needed to store a TPG is around 100 kilobytes, while for similar performance, you need more than 50 megabytes for a deep Q-learning network. So let's come back to our implementation problem, because our purpose is to provide a library that implements TPG in a lightweight way. And one of our key objectives was for this library to be deterministic and parallel. Why determinist? Because determinism is a very good property when you have an embedded reinforcement learning library. It enables you to port an algorithm to train an algorithm on your computer and then deploy it on an embedded target. It facilitates the reproducibility of the results that you get. If you get good results on the computer, you will get them everywhere else. And it's also a great feature for debuggability. Then parallelism. Why do we need parallelism? Well, for 3 reasons: performance, performance, and performance. Performance of training, performance of inference, and performance of both combined. Unfortunately, parallelism and determinism do not go well together. When you try to design the parallel software, it will very often not be fully deterministic, and deterministic comes usually with sequentialism. So how will we achieve this purpose? To do that, first, let's see how we can get some sequential determinism. First of all, we need a pseudo-random number generator. A pseudo-random generator is a process to which you give a seed, a number, and from this seed, it will generate a sequence of apparently random number, but in reality, completely deterministic ones. So we use this pseudo-number generator in the genetic evolution process. And so the genetic evolution process, which is responsible for mutating the programs of the TPG, will ask pseudo-random number to the PRNG. And again, we use the pseudo-random number generator for the evaluation process when randomness is needed in the evolution of the state of the environment. So this is how we do things sequentially. And then we can repeat the genetic evolution process, then the evaluation process several times to train our TPG. Unfortunately, what we want is parallelism. So let's see how we can achieve parallelism in a completely non-deterministic way. And this is the most naive way to get some parallelism. We just duplicate the genetic evolution process. And we give one instance of this process to each core of our target architecture. Because each one of the genetic evolution process will work on a different program in parallel in a non-deterministic order, they will keep asking pseudo-random numbers to the pseudo-random number generator in a non-deterministic way. And so you have non-deterministic mutations that are applied to the program. And the same is true for the evaluation process of the roots. You cannot have a deterministic process. So how do we get determinism? Well, the trick that we used to get determinism is to associate a pseudo-random number generator to each instance of the genetic evolution process. Using the main sequential PRNG, we give a seed to each one of these parallel pseudo-random number generation, and we actually give one seed for each program. And by doing that, we can make sure that the mutations that are applied to each one of the programs during the training process are completely deterministic, because the seed that is used to initialize the pseudo-random number generator of the parallel processes is itself determinist. And the same is true for the evaluation process. We just generate one seed for each root of the graph that is evaluated. So all of this has an overhead on performance, but as we can see on this first result, which is the speed up that we get. So on the abscissa, you have the number of cores that are used for the training process of a TPG. And on the ordinates, you have the speed up that we get when we go multi-core. And as we can see, the process, the parallel training process scales very well. And we get performance that are 20 times better on 24 cores than we got on one core, on an Intel core, on an Intel CPU with 24 cores. So this scales almost perfectly. What about an embedded target? Let's have a look at the Odroid XU3, which embeds an ARM Big Little architecture with 4 A15 cores. So on the A15 cores, we have a speed up of 2.3 on 4 cores, sorry, which in reality is limited by the bandwidth of the memory. We had a look at the result, and it seems like the memory is the limiting factor here. If we activate the A7 cores, then we can first see that on one A7 core, the performance is roughly half of one A15 cores. But the performance on the 4 A7 cores scales very well, and we get a speed up of 4 compared to one A7 cores when we activate the 4 A7 cores. Then we can activate any combinations of the A15 or the A7 cores. And the best speed up that we can get compared to a single A15 core is a speed up of 4.1, which once again on this chip is limited by the bandwidth of the memory. So to summarize, JJLATI, which is the library, the name of the TPG library that we have implemented, is a TPG framework for training, executing, and customizing learning artificial intelligence based on the TPG model. JJLATI is developed as a C++ library, which is both portable and deterministic. It works on Windows, Linux, and Mac OS. It is fully open source. The code is fully documented, and we have a very important continuous integration process, which ensures that we have 100% of the code that is covered by the unitary tests. We have some good features. We have some multi-core support, some custom instructions that are detailed in the paper, and many more to come, hopefully. We have several applications that you can already play with online. So we have the Atari video games. We have a physical inverted pendulum that you can play with, the MNIST classification problem, the tic-tac-toe two-player game. And we also have a robotic controller for a robotic arm with 6 servo motors. So almost on time. Thank you all for your attention. If you are curious about JJLATI, you can check out the GitHub pages of the project. And otherwise, if you do not have questions right now, which I would be very happy to have, you can always contact me later to my email. So thank you for your attention.
Thank you, Karol, for the very interesting talk. Maybe if I can start, because I have one question. Where is the drawback here in this whole story? Because as you talked about this, it's a new thing for me. It's like everything is better than the deep approach. So is there any drawback here, or?
Yes and no. Okay. One drawback that I can mention is that, okay, we have very good results on the Atari video games. On the robotic arm and the inverted pendulum, we have very good results also. On the MNIST classification problem, so far the results are not so good. We are not able to compete with the deep learning framework. So it seems like the TPGs so far are very good for the reinforcement learning problems. For other kinds of problem, we have ideas of why they are not working very well, but we still have to improve them. For the other one, okay, compared to deep learning on these, let's say, quite simple problems, you're right, they have only advantages. They have no drawbacks. They perform very well as the deep learning framework. And they are more lightweight. It's faster to train them. So no, it's true that they are better in all aspects. If we really want to find some drawbacks, yes, for example, on the Atari video games, since the publication of the early results that showed that TPG were competing in performance with the deep learning framework, Agent 57 has been published, which is a deep learning approach that is better than any previous attempt to these video games, and it beats also the TPG's attempt. But this comes at the cost of a huge complexity in the training process and in the inference process. So once again, the trade-off offered by TPG between complexity and efficiency is great.
Okay, thank you. We have also one question from Eduardo de la Torre, or actually 2 questions. I will read maybe. First, nice work, Carol, and the questions. How well or bad does this scale up with increased complexity? It's the first question. And the second, have you tried crossover apart of mutation?
Okay, so for the scaling process, it scales pretty well. When you train a graph, you can see that the training process slows down when the graph becomes complex. But actually, this slowdown is not that huge. And the time, for example, on the Atari video games, the time it takes to train the TPG is still largely dominated by the emulation process for the video games. So the TPGs itself, the structure of the TPG is very simple. And even when the complexity of the TPG increases, which means graph with, let's say, at most hundreds of teams and hundreds of programs, it's still very, very fast to execute the TPGs. So the complexity is not a very big issue on the TPG side, even on complex problems. And about the crossover, no, not yet. At the moment, the only mutations that we tried were random mutations of the programs. So we swap instructions, we change instructions, we replace an addition by multiplications. But so far we did not try the crossover operation. We want to have a look into it, but we have this MNIST problem that is very interesting for us, and that we really are focusing on this right now.
Okay, thank you very much. I think we can have an interesting discussion on this issue also later. I'm personally also interested in this approach. Or maybe not I personally, but one of my PhD students should be. Thank you once more. And now to the last speaker, or actually 2 speakers of this session. So could you stop sharing, Carol?
I think I stopped.
Okay, and now Joanna and Konrad.
Hello.
Are you there? Okay.
Can you hear us well?
Yes, yes, you can start sharing. I'll introduce. Joanna, Stanisz and Konrad Lis are PhD students also from my research group. And their research areas includes embedded vision systems and autonomous vehicles perception systems. And they, from their beginning of our cooperation, so from the first bachelor and then master thesis, and now on the PhD, they are working on LiDAR data processing. And so the presentation is also about implementation of LiDAR deep neural network for LiDAR point cloud data processing. So please present.
Thank you for the introduction. So we will present our project, hardware software implementation of the point pillars network for 3D object detection in point clouds. The object detection task is a vastly explored subject in the scientific society. It has various applications, including autonomous vehicle perception systems, ADAS, that is Advanced Driver Assistance Systems, object tracking systems, and also autonomous unmanned aerial vehicles perception systems. In the aforementioned applications, the detection accuracy and real-time operation is critical for safety. An autonomous vehicle is equipped with several sensors, and that is GPS, ultrasonic sensors, radars, cameras, lidars, and each of them has its own advantages and limitations. The lidar sensor provides an accurate reflection of the car's surroundings and is robust in various lighting conditions. It is more and more popular subject for academic research. Also, its price is expected to drop drastically in the near future.
The object detection system in vehicles are critical for safety. It implies that they have to provide high detection accuracy alongside with real-time processing. Vehicles are off-grid systems, so we have to use embedded devices to keep the power consumption low. Currently, the most accurate detectors are based on deep neural networks. DNNs are computationally complex and often consume large memory resources. In order to provide real-time processing and enable implementation on an embedded device, they have to be optimized. The aim of this work is the hardware-software implementation of the point pillars network to detect objects in 3D point clouds obtained by a LiDAR sensor. The Kitty database was used in the work. It provides data from 4 cameras, LiDAR point clouds, and GPS data. Kitty also maintains an algorithm evaluation ranking in a couple of categories, including detection of cars, pedestrian, and cyclists in both 3D and bird's eye view. In this object detection task, there are 3 difficulty levels: easy, medium, and hard. Having analyzed a couple of object detection papers, we focus our attention on point pillars network. The network can be split into 3 main parts: pillar feature net, backbone, and detection head. Point pillars network divides the input point cloud into a set of pillars without preset height. Pillar feature net is responsible for calculating feature for each pillar. The PFN generates a pseudo image by putting these features to proper position in the output tensor. The backbone contains mostly convolutional and transposed convolutional layers, and the detection head is responsible for detecting and localizing objects in the point cloud. It is based on a single-shot detector.
In the May 2020, the best 3D object detection method was PV-RCNN. Point pillars has circa 10% smaller detection accuracy in all 3 difficulty categories. And most of the high accuracy methods include atypical, complicated operations that are hard for hardware implementation. The point pillars, however, offers a good compromise between detection accuracy and the complexity. And this is why it was chosen for implementation in this work. A deep neural network can be optimized in 3 ways. Firstly, we can change its architecture, and that is remove or change some of its layers. This allows to reduce network size and computational complexity. However, there is a high risk of large accuracy drop. Secondly, it can be pruned. It means that a part of its weights can be zeroed, usually with little impact on detection accuracy. The zeroed weights don't have to be stored, so the overall model size is smaller. In the FPGA, it can potentially result in smaller logic resources consumption. And finally, the network can be quantized. In default, the DNN computations are done on floating point values. The aim of quantization is to change floating points to fixed point computations. It reduces the model size as well as enables implementation on FPGA devices.
The network quantization was performed using Xilinx Brevitas library. It includes quantized linear and convolutional layers, as well as quantized activations. The target network implementation was obtained using Xilinx Fin tool. Among others, it supports quantized fully connected and convolutional layers, as well as quantized activations.
The quantization experiments were described in our previous work. Here we will only quickly present methodology and results. We started with a floating point network. Then in 4 stages, we chosen quantization types of consecutive network parts. Firstly, we quantized the backbone, then PFN, detection head, and activations at the end. In the lower part of the slide, you can see a table with quantized network average precisions. The consecutive quantization types in the first column rows concern PFN, backbone, detection head, and activations. The final quantized network version is the one at the top. Its detection accuracy, compared to the floating point one, dropped by a maximum of 9%. To implement the point pillars with the Fin, we had to make modifications both to the Fin tool and to the point pillars network. Firstly, only backbone and detection head were implemented in the programmable logic. The PFN and scatter operation had to be moved to the PS. It is because Fin do not support scatter operation, which is atypical one. The common Fin implementation scenario assumes one continuous neural network with no unsupported operations in the middle. And our network have 2 such continuous parts, that is PFN and backbone combined with detection head. The latter is larger, so we decided to implement it in hardware as it has better acceleration potential. Second, we had to move transposed convolutional layers, and we had to remove transposed convolutional layers and some of the convolutional layers. The former were removed because Fin does not support them, and the latter were removed because initially the implementation utilized too much FPGA resources, and we had to reduce the network architecture. Third, the quantization types were changed compared to the quantization types we obtained after quantization experiments. It is because we had to modify it to meet Fin and programmable logic resources constraints. And fourth, Fin was adjusted on source code level to make it work with our network architecture. In our work, we used Fin version 0.3 beta with modifications, but Fin is still under development, and version 0.3 beta did not support some of the features that were necessary for us. For example, 2-bit activations. The issues we bumped into may already have been rectified in current new Fin version 0.5 beta.
As a target platform, we chose an ZTU-104 board. The proposed system was partitioned between processing system PS, programmable logic PL, and a PC. We will briefly describe consecutive elements of the system. At the beginning, the PC sends to PS a data indicator. It is a number of point cloud, which PS is supposed to read from the SD card. The processor reads point clouds from SD card, voxelizes them, and extends feature vector for each point. Data prepared in this way is fed into pillar feature net. Then a scatter operation is performed. It collects PFN outputs vector and puts them into backbone input tensor. The backbone input is preprocessed and sent to the programmable logic. There is processed by backbone at detection head. Output classification and regression maps are sent to the PS and post-process. Finally, processor sends output maps to PC, which interprets them and visualizes.
On this slide, we present detections obtained from the target platform. At the top, you can see car detection projected on camera image, And at the bottom, you can see the same detections in point cloud from bird's eye view. Results. The system has been run on the ZCU 104 platform with Zenk UltraScale plus MPSoC. To do this, we had to introduce some simplifications. We finally obtained maximum of 19% average precision drop in comparison to original floating point network and 55 times network size reduction. One point cloud processing takes about 20 seconds, where 2 seconds go for programmable logic and 80 seconds for processing system. It is far from real time, but we are already working on time optimization. Resource utilization is as follows: 62% of LUTs, 18% of flip-flops, 49% of block RAM slices, and none of the DSPs were used. Maximum measured power consumption is slightly above 12 watts. Modern GPUs take at least 100 watts, so our system is more efficient by an order of magnitude. Future work includes time optimization of the hardware-software network implementation, creating a demonstrator cooperating with a LiDAR sensor, experiment with Kitty object classes, with other Kitty object classes and other data sets, experiments with point pillar architecture modifications, and data fusion with other sensors, it is radars and cameras. Thanks for your attention.
Thanks for the presentation. So we have 5 minutes for questions.
Thomas?
Yes.
Okay, I don't know if you can hear me. Just a place for a question, or we are late?
No, we have 5 minutes for the questions.
Thank you for the presentation. Just one question. I have missed the last part of the presentation because I have a little problem with my connection. In your implementation, you say that there is only a part that you have developed in the programmable logic of the network. Do you have compared a full version that run on a processor system compared with your version that you have deported the part of the in the programmable logic? If there is I don't know, an improvement, the speed of or in the performances of the neural networks?
I don't know if I understood your
question. If you have in your, for example, you take this slide in your design, if you have tried to implement all the neural network inference model algorithm in the PS part of the pink, and after compare the performances in terms of latency, in terms of precision, with your version that you have implemented a part in the programmable logic of the neural network?
We haven't tried to implement the whole neural network in the PS. We have compared this. Actually, we have compared the quantization, quantized network on the PC, and with the floating point version PC only. We have only run this in the target platform, we have only run this version of the network. We haven't focused on relocating on experiments with backbone and detection head in the PS or PFN relocation to the PL, because we have struggled with the performance issues of the backbone and SSD in the PL, because this one network run in the PL takes about 2 seconds, where it should take less than 1/10 of a second. So it is the main problem we have, and we have focused on it in our work.
Okay, thank you very much.
Just to conclude, I can maybe add something even more interesting, or for us also difficult. Just recently, Xilinx in its tool VTS AI, they provided an example design of the point pillars network, and this works in real time as far as we know, and we even tried it. And now we are working on where is the problem exactly, because from the theoretical point of view, this thin framework should work at least the same as the VTS AI framework. However, they have different principles of operation. So even the thin framework should be more efficient or use less resources. On the other hand, with this network we had many problems. So that's one of our currently investigated issues. Yes. If anyone would just use thin, then be prepared for such things.
Hi, this is Benno Stabernack. I have basically 2 questions regarding the power consumption. How did you measure the overall power consumption, and could you say what's the most power consuming part of your implementation?
It is the PS FPGA. The programmable logic part consumes about 4 or 5 watts, and the PS consumes more. The overall is 12 watts. Yeah.
Mm-hmm. Okay, and you measured the overall board power consumption?
Yes, it is.
And it's not simulated. Okay, do you see any room for improvement there, or?
To be honest, we didn't think about this.
Okay.
Yes, I think 20 watts is not much. Maybe it can be reduced, but it's not a. The GPUs are more inefficient.
Sure.
Yeah.
I know that. Okay, many thanks for the answers and for the nice presentation here.
Thanks.
Thanks. There is also a question or a raised hand from Eduardo de la Torre. Or maybe this was the previous thing. Oh. Anyway, I think we have now 1 hour lunch break. Then there is this keynote, the general keynote. And we will come back at 15 0 with the last session, and then with, sorry, this our discussion. I see that there's some questions or some issues. Some of you placed some comments to the papers. Now mainly Karol Jejelati work is drawing some interest, I see. But anyway, you can think during the lunch if there is something we should be clarified and so on. And see you then in 2 hours.
Yes. Hello, everyone. Okay. Good afternoon.
Yes, yes. So Alamech is a third-year PhD student at the University of South Brittany in France. She holds a master's degree in computer system architecture from the Science and Research University of Tehran, and her main research interest is multiprocessor architecture, memory and data flow, machine learning, and deep learning applications. And today she will tell us a little bit on cache limits for data flow applications and related efficient memory management strategies. So Zoom is yours.
Yes, thank you, Thomas, for the introduction. So let me, do you have my screen?
Yes.
Okay.
Yes.
Yes.
Okay, thanks. The title of our work is Uncache Limits for Data Flow Application and Related Efficient Memory Management Strategies. This is the outline of my presentation. First, I start with the introduction. Recently, multi-core architectures has encountered with different challenges in hardware and software. In hardware side, with pressure in memory subsystem, which mitigated by cache hierarchy, and in software side, parallel programmability that helped by parallel languages and tools. Data flow model of computation, which has been already presented in this morning presentations, in previous presentations, bridges the gap between the application and multi-core platform. By specifying, in fact, by specifying the parallelism in spatial and temporal, it helps the application to fully exploit the hardware parallel resources, in which the application is defined by a graph of processing elements communicating via the FIFOs, generating and consuming the data tokens of FIFOs. Static data flow models allow the application be optimally scheduled. In fact, the goal of our work is to demonstrate that in a general purpose multi-core architecture with cache hierarchy, even data flow applications optimally scheduled and mapped the execution time cannot scale up well by increasing the number of cores, size of caches, and factor of cache sharing. Basically, our contribution is in 2 parts. The first is evaluation of the behavior of data flow applications over different cache configurations. And the second is proposing memory management solution for generating data flow application. For the experiment, we explored the 2 computer vision applications, stabilization filter and stereo matching algorithm, which is for generating 3D images. Challenging feature of stereo in memory usage in cache locality makes it good candidate for evaluating for our evaluation of cache behavior. Our applications are generated by Prism framework in C code, and we use workload-based mapping for the application. For For the baseline architecture, we consider the multi-core architecture with up to 3 levels of cache that interconnected via the network and chip. The platform is simulated by a functional multi-core simulator Sniper. We explored 22 different cache configurations by changing the factors of cache size, cache sharing, and the number of controllers. For L2 and L3, we considered as maximum size 4 megabytes and 256 megabytes respectively, which is not available realistically in the current desktop computers. For the number of cores, we increased up to 32 and the number of controllers up to 8. Here in this table, you can see 2 examples of our configuration, number 5 and number 10, in which the number 5, L2 and L3 are private, and number 10, L2 is shared by 2 and L3 is shared by 8, and total available cache size is like this. So this figure depicts the results of the performance for the applications. Vertical axis represents the execution time, and the horizontal axis shows the different cache configurations. The bar charts with the stars shows the best execution time in each configuration. By increasing the number of cores, as expected, the stabilization has upward performance, but stereo has shown a different behavior. As a stabilization, total FIFO size can fit into the cache hierarchy, so it scales well. But for a stereo, as total size of FIFO is 500 megabytes, it cannot fit into the cache hierarchy, so it doesn't scale up well. We have 3 different trends for the performance. The first one is from 4 to 8, the upward performance, which both of the applications showed improvement. So distributing more actors over the over more number of cores results in more available cache, more available space in the L1D cache for each actor. So we decrease the cache miss for the actors. We receive the performance. But the trend of performance slows down from the 8 to 16 trend. Okay, sorry. Now, because we have a penalty of losing data cache locality by distributing more the actors over the core. The more we share the cache, we can see the impact of the cache controller is considerable. The last trend is 16 to 32, that 2 applications show different behavior. For the stabilization, it showed improvement in the execution time, despite the stereo that the execution time got worse. In fact, the stabilization benefits from cache sharing because for the total mem copy of the for total mem copy, we need around 800 KB memory access, which can fit into the cache L2 cache when it is shared. But for a stereo, even a stereo as FIFO copy needs around 500 megabytes. So even sharing doesn't help a lot. So it doesn't have any tendency to sharing or private. Here you can see the DRAM access by increasing the number of controller over different cache configuration. each time that we have less number of controllers, you can see the spike of DRAM access. This behavior is the same in this application, but it works for the stereo application. So you can see that the stereo application is a demanding application for the DRAM, and it is limited by the memory controllers. Here is the list of our findings. The first is bigger cache not always help, and both applications are limited by the data cache miss rates. And the PRIS framework uses memcopy for sharing the FIFO, for broadcasting the FIFOs and also round buffer actors, which really negates the cache hierarchy. So we propose to the new solution for the memcopy of the FIFOs. Our first solution is copy on write. What we do is that, in fact, we just duplicate the FIFOs in case of any write. So we use a map function instead of memcopy with attributes of shared memory open and map private. In our experiment for a stereo with memcopy, usually we have 19 copies of 9 megabyte FIFOs, but by using our approach, we have just single copy of 9 megabyte FIFO. And the second, and for a stereo, we have just one copy of this UVido. For our evaluation, we used a sniper, but as a sniper has limitation in modeling the operating system, we use user level and kernel level simulation. We use these two configurations with 8 and 264 megabyte total cache size available. And for the results, so we have decreased the number of L1 accesses up to 60% for stereo, and we received a speed up to 2 for memcopy. And as we used a map is has an overhead of delay for the configuration number 4, which is really limited by DRAM delay. We couldn't receive more than 1.6 speed up. So our solution helps the stereo a lot because the stereo is more memory starved, and we received a lot L1 access reduction and speed up. So the second solution is non-temporal memory, which use directly copy into the DRAM by RAM to RAM DMA or bypassing the cache hierarchy. This method has a lot overhead in speed, which is speed is half of the memcopy. So for transferring the size more than 8 megabyte, the speed is half of memcopy. And so as a sniper doesn't support non-temporal memory, doesn't support non-temporal memory, we did our experiment over Xeon Silver with 32 cores and L1 and L2 cache with size of 64 KB and 1 megabyte size, and 13 megabyte for the L3. So as a result, we could reduce the data cache size up to 38% and TLB miss up to 65%. So as NTM has around 23% of instruction overhead, so it's not surprised that we didn't receive any speed up. So here is the related work. Our Our work covers a static data flow application, and our solution results in reduction in cache pollution. And we consider general purpose architecture with cache code with legacy code compatibility. As a conclusion, we evaluated two data flow applications and 22 different cache configurations. Both applications showed poor cache localities. And we proposed to solution for memcopy that data flow could fully benefit from the cache hierarchy. Our experiment showed the reduction of the cache miss rate up to 60% and the speed up to 2 without changing the source code of the actors. Thank you for your attention, and for the question, don't hesitate to ask. Thank you.
Thank you very much. So if there are any questions, feel free to ask.
If I may, I have a question.
Yes, sure.
Okay, so of course, before I tell the question, I have to say that I, of course, know very well the applications you are talking about because I'm the one who coded them. So this might be the reason for my question. When you mentioned the stereo matching with a footprint of 500 megabytes, this means that you have used absolutely no in-place memory optimization, advanced, let's say, memory optimization of the Prism framework, which allows the tool to reduce the memory footprint to 50 megabytes, let's say. And so this is the first question. And the second benefit of these optimizations that are available in the tool is that most of the memcopy operations are removed. And the buffers that are co-allocated. So all the issues that you mentioned with the broadcasts that duplicate the data in several FIFOs is already covered by these optimizations. So my question is, did you try this optimization and what were the results? How did it improve the cache efficiency? Because from our experiments in previous paper and also with the distributed memorification, we saw that it was already improving the cache efficiency. So my question is, did you try them? And if not, is there a reason why?
Yeah, and for the Prism, we use the default configuration of the framework. So we generate the code with default configuration, and if it is not applied, so we didn't use it by default. I mean that there are some memory management in the Prism framework for removing the this memcopy. Am I right now?
Yes, absolutely. I think you might want to have a look at it. It's available on the website. You have a tutorial dedicated to it. It's advanced memory optimization.
Okay, thank you. So
everything is there to remove most of the memcopy generated by the broadcast or the fork and join operations.
Okay, thank you. Yes, sure. I will see. Thank you. Thank you. And did I answer all your questions?
Actually, I had a question.
Yes.
In your conclusion, you said, let's see if I can see, yeah, the non-temporal memory transfer. You said that so that the data flow methodology can fully enjoy the benefits of the cache hierarchy, but maybe I didn't understand it. When you talked about non-temporal memory transfer, you mentioned instructions that bypass the cache.
Yes.
So how is it then benefiting the cache hierarchy? I didn't fully get that link between those two.
Because we found that by using a lot of memcopy, which exactly make duplicate the big FIFOs, so it polluted the cache hierarchy a lot. So that's why that we just try to bypass the cache in case of write. Just write into, because write into the DRAM instead in case of the write. It is exactly pointing to the FIFO just for write, not for read, and accessing accessing for to the cache for read.
Okay. Yeah. Now I understand. Yes. Okay. Thank you.
Okay, so when there are other questions, then just after this session, we have this discussion. So thank you once more. And now we can proceed with the second presentation.
Okay, so
we can stop sharing, and I invite Krzysztof. Yes.
Okay, hello together. Can you hear me? Can you see me?
Yes, we can see you, we can hear you. Krzysztof is
Perfect.
a PhD student at Technical University Darmstadt in the Embedded System Application Group, and his current research focuses on real-time fine granular control flow and data flow integrity enforcements for IoT class devices. And before, he contributed an approach for estimating the critical path of highly heterogeneous coarse-grained reconfigurable architectures. So the presentation, the floor is yours.
Okay, hello from me and welcome together. Thanks for the introduction. My name is Krzysztof Blachut. I'm working at TU Darmstadt Embedded Systems and Applications Group, and my colleagues are Yannick Lavan, Marco Hartmann, who is also here today, Florian Meisel, and Andreas Koch. I'm presenting DAXI, the Dynamic Execution and Integrity Engine, which is an IoT class hardware monitor for enforcing real-time fine-grained control flow integrity. I will begin with the security scenario. So here we have a real-time IoT device which has dangerous security critical periphery attached via memory mapped I/O, and this periphery can be a smart lock which the attacker tries to open, an industrial robot which can be manipulated, or a smartphone. So let's continue with the attacker model. The attacker can alter control flow instructions via code reuse attacks. This includes return into libc attacks and return-oriented programming attacks. These two attacks are tampering with return addresses. Tampering with return addresses can be mitigated by validating return addresses at return time, and this can be done, for example, using a shadow stack. We are also including jump-oriented programming attacks, which tamper with function local control flow instructions. And these type of attacks can be mitigated by enforcing control flow graph integrity. Now I'm continuing with the security guarantees. So DAXI guarantees to react to any control flow instruction violating the currently active control flow constraints, and DAXI does so within guaranteed time. Therefore, DAXI will block any sequentially or ongoing MMIO write instruction following the illegal control flow instruction. So here we have the control flow instruction within the RISC-V core within the execute stage, and there's the illegal data flow instruction writing to the MMIO. And this can be far away, this can be closer, or in the worst case, this is back-to-back to our control flow instruction, which is manipulated. And DAXI guarantees that the read instruction is not committed within the memory stage. So our assumptions, we are not covering code injections. What is a code injection? Code injection means that the attacker replaces the original code with the attacker's code. So for mitigating code injection, one can use a memory protection unit, data execution prevention, read-only memory or memory management units. So there are a lot of measures to mitigate these type of attacks. So next I'm talking about software-hardware partitioning. Control flow integrity can be realized as software-only, hardware-assisted, or hardware-only. I will begin with the software-only approach. When doing everything in software, one needs to add additional instruction, for example, to save the return address after a function call and to check the return address before actually returning. So this is relatively easy, but depending on the granularity, especially if you also want to consider the function internal control flow, this comes with a high overhead, depending on the implementation. Next is the hardware-assisted control flow integrity approach. Typically, one uses a second guard processor with the size about the first main processor core, and the guard processor supervises the execution within the main processor core. So this comes with twice the logic overhead, but is typically faster than the software-only approach. And finally, there's the hardware-only approach. There we have a hardware integrity unit, which supervises the main processor core again. And this hardware integrity unit is typically smaller than the second core approach and comes with additional benefits, for example, real-time capability. So this is what we are doing. We are implementing a hardware integrity unit with real-time capability, which comes attached to the processor. Next, I'm considering the actual location of our hardware integrity unit. This unit can be located within the pipeline. This yields lowest latency, but also comes with lowest portability, as it is highly matched to the pipeline structure. Then the next location is on-chip, but out of pipeline. This comes typically with slightly increased latency and still good portability. And the third option is an off-chip solution with best portability, as the system on chip does not need to be changed. This comes with very long latency because the interface here is typically relatively slow when compared to the processor, and it comes with a throughput limitation. So here we are choosing the second way because in our eyes it's the best trade-off between latency and portability. Next, I'm talking about monitoring and enforcement. So I will begin with monitoring. On the left side, you again see the RISC-V core, and on the right side, the monitoring unit. The monitoring unit here observes fully committed instructions. So this is a one-way flow of observations, and the monitoring unit passively monitors these violations. There's no way of interacting and stopping, preventing the attacker. Next, I'm comparing this monitoring with enforcement. So for enforcement, we have a closed loop operation, and we can actually prevent attacks from happening. Therefore, we require signal taps in early pipeline stages, which observe now uncommitted instructions, and they are forwarded to the enforcement unit, which in our case is DASIP, and which then has limited time to actually prevent the attack from happening, and this can be done via stalling, resetting, or interrupting the execution. Now I'm comparing the parallelism level of execution and checking. I will begin with the serial execution and checking flow. So when running serial, the program execution will be stalled each time there's a control flow instruction, and during the program execution and when the program execution is stalled, the control flow evaluation runs exclusively. So this requires additional clock cycles, and this translates into runtime overhead. Next, there's the fully parallel approach, where the evaluation always runs in parallel to the execution. There we do not require additional pipeline stalls, but this is hard to achieve because timing here is difficult, because one must guarantee that evaluation is always as fast as execution or even faster. Finally, there's the hybrid approach. The idea is make the common case fast. For typical control flow instruction, this means there are no stalls required, but in case of rare control flow instruction or edge cases, one might require stalling the execution and require additional time until the checking is complete. So here we're doing the parallel or hybrid approach depending on the RISC-V core, which is attached to our control flow integrity unit. Now I'm again referring to the worst case attack scenario. So the worst case is if the control flow instruction comes back-to-back directly with the evil memory mapped IO instruction. So there we have minimum time to react. When the control flow instruction now enters the execute stage, it's already forwarded to the enforcement unit within, which then has 1 clock cycle time to react. And in this case, it resets the RISC-V processor such that the evil memory mapped IO write is not committed within the memory stage. In this simplified example, we are not using any storage, but depending on the pipeline structure and depending on the enforcement unit, storage can be required here. So now I am talking about our major challenges when implementing this. So the major challenge, of course, is speed and real-time capability. We'd like to avoid storage, and we also want to avoid a long critical path. At the same time, we must guarantee that we are fast enough to block any subsequent and memory mapped IO write. Additionally, we'd like to be compatible to a high number of RISC-V cores, and we must be efficient because embedded or IoT devices don't have unlimited power available. Especially efficiency gives us constraints for the memory storage, and depending on the program structure, this can be almost random access if there's a large number of valid control flow targets at the same time. We're not using caching because caching is against our real-time requirements. We need a memory with very low latency, below or equal 1 clock cycle, as I've shown before. And we require a tight memory layout because SRAM or BRAM on the FPGA is quite expensive. So here's our solution, which is a hierarchy of finite state machines. On the left side, you see the program code, C code, and next to it, the RISC-V assembly code. For the C code, there's the main function with a branch instruction, the if here, and we have a function called to the upper function, which then finally has the return instruction returning to the main function. And for the RISC-V assembly corresponding to the code, we have the branch of equals 0 at 0x17c, and which has 2 valid targets, 0x180 and 0x184, the taken or untaken branch. Using static analysis tools we implemented, we are automatically generating function local finite state machines from out the RISC-V assembly code. And for the first function, this translates into a finite state machine with one finite state, with one state, because there's no control flow instruction except the return. And for the main function, we are using the two-chain generates a finite state machine with 3 states. Here is the branch instruction with the untaken and taken branch, again, yellow and green, and the call instruction here in purple. Now next, our two-chain splits this call into the call and return, and then automatically also generates the hierarchy of FSMs with the call and return. And there we have a hierarchy of FSMs which corresponds to our initial RISC-V assembly code. We are using an FSM-aware shadow stack to guarantee that we are returning in the correct FSM, correct state, and to the correct address. Here I'd like to talk again about our memory. On the left side, you can see the transition table holding transitions, a number of transitions for a number of functions. So you can imagine that there will be a high number of transitions for large applications. Therefore, we desire to reduce the number of bits required for each transition, and therefore we added a layer of indirection, which is the local and the global address mapping, which maps the wide local or global addresses to narrow address IDs, therefore reduces the width of the transition table, and therefore reduces the overall memory overhead. So finally, I'm talking about the evaluation, and I will begin with the clock frequency cost. As you can see, with on the left side, you can see the VEX RISC-V core, Tiger, Pico RV32, and Piccolo. And without DEXI, Pico RV32 goes up to 340 megahertz on the Xilinx VC709 evaluation board. With DEXI, we are limited to 145 megahertz, which is, depending on the RISC-V core, is a large frequency drop. So What you see here is that we are using DEXI with identical parameterization for all cores. As part of our future work, we aim to trade critical path versus clock cycles to improve the clock frequency drop here. But what you also can see is that the best case, Piccolo, we have even a small performance improvement, and we are not limited to 145 megahertz. And right now, this performance improvement is not related to DEXI, but it's related to Vivado, because somehow Vivado, Xilinx Vivado, found a better routing and placement when Piccolo is combined with DEXI. So this is not related to DEXI. So next, I'm talking about the area cost. For BRAM, it's between 4,4 and 12,1% memory overhead, which is very good for a fine granular control flow integrity solution. The register overhead is between 65 and 108,5%, which is also quite good, but not yet fully optimized. And the LUT overhead is between 15,8 and 124,3%. So we are often smaller than the second core approach. So now I'm talking about wall clock execution time, because that's the only one, the performance which counts. And this performance is impacted or is affected by the frequency slowdown, but also by the percentage of additional storage cycles. For VexRISC-V, this is minus 74%. For Tiger, the one-time slowdown is about 50%. In the worst case is Pico every 32 with 134,5%. And the best case is Piccolo, which also has a performance improvement, but as already said, this is related to Vivado and not related to DEXI. So when talking about the number of statical predictable storage cycles, which of course affects the wall clock execution time, the worst case is Tiger, which is up to 10,4%, and this is because Tiger has partially independent execution units and a rather flexible pipeline structure, and therefore requires additional storage. And the best case here is Pico every 32, which does not require any storage at all, because Pico every 32 grants us enough evaluation time such that no storage are required. So here, I'd like to conclude that DEXI is real-time capable and all stores are statically predictable for worst case execution time, and we are not using any caches. Therefore, that's always the same execution time. DEXI is generally faster than the software instrumented code solution, and DEXI is portable. We have shown 4 RISC-V cores, and DEXI can be easily attached to a number of RISC-V processors. DEXI is typically smaller than the second guard processor approach, and depending on the FSMs provided to DEXI, DEXI can enforce variable control flow integrity levels. So thanks for listening. Do you have any questions?
Thank you very much.
Thank you. I have a question, but if there is other person that would like to start, I can make my question at last.
Okay, I don't see the questions right now. Just start.
For the instance, there is no question in the reserved area for question, and so if there is any person that would like to ask directly without tapping the text of the question, waiting, I can start with some questions from my side. Thank you very much for your presentation. It's really interesting. I have just a few questions about your last slide about performances. Perhaps I missed it, but when you evaluated the different RISC-V architecture, and you have made an implementation in which kind of Xilinx device, which is the device targeted?
We are using Xilinx VC709 evaluation board, and
okay. And so the question beside is, you don't think that the performance that you announced depend strongly on the platform that you have chosen for the implementation?
Exact.
So if you come back to your slide in the frequency performances.
Yeah, this one.
Yeah. Did you have evaluated the same, but in terms of number of cycle of clock and not in terms of frequency, these performances?
Yeah, on the one hand, I evaluated the number of clock cycles required, and also I evaluated the number of the frequency drop, and I evaluated the overall wall clock time. This is what we were doing, and yeah, they have.
Okay. In term of number of cycle of clock, the result are the same. For example, for Piccolo, you have also always the same, not difference between with DE and only core.
For Pico every 32, there were no starts at all, and there were no difference between the clock cycles. And for checking that we always have the same runtime. For example, Tiger has a number of star cycles which are introduced by DEXI, and we run it several times, and always we had the same number of overall clock cycles required to run the execution. So this is what we checked. So when you run the application once and you measure how much time you require, you will know how long it will require always. So there's no tolerance. It requires exactly this number of clock cycles.
Okay, and the last question after perhaps order if I have time, but when you talk about in the next slide, I think about BRAM occupation.
Yeah.
BRAM overhead. If you have analyzed which is in terms of the device, because each device have different sites of BRAM, which is the method to choose the good sites of the BRAM that could optimize the implementation of the RISC-V architecture.
Sorry, could you please repeat the question?
Yes, if
so
you can, with this kind of analysis, if you have find which could be the best sites of the BRAM that we can try. We needed to choose which the FPGA device we needed to choose to make our implementation, to implement our design. Each device have different sites of BRAM. If there is how we can choose, how we can know we can have the good performances, we targeting the good device with the good sites of BRAM, which is the good sites for this kind of.
So if I understand you correctly, you want to choose a FPGA device with large on-chip BRAM memory.
Yeah, in terms of in function with I don't know. I need to implement I don't know VEX RISC-V architecture. I know that in your design that you have implemented, you have a BRAM overhead about 10. It's correct. And so how I needed to redesign my I need to change device or not?
So I'm not sure about the answer right now, but we used the VC7R9, and even with DEXI, we had still plenty of BRAM. We were like 15% or something usage for the VC7R9 device. So you can easily use this device and you will not run into memory problems.
Okay.
Maybe this answers your question.
Yes.
So for example, you can use this device and you will have plenty of memory. This will easily work out.
Okay. Okay.
Maybe I can add that we are using the Tabasco Task Parallel System Composer framework here, and we implemented everything in BlueSpec. And this allows you to easily change the FPGA board, and maybe as future work, and I can evaluate this.
Okay. Thank you.
Thank you also.
Okay. Okay.
No.
Yes, please.
No. If you were to, you were talking about 3 grades of how tightly coupled it is, right? And I believe you chose the middle path. How much do you think you could improve performance or improve? Yes, here the on-chip. That's the one you chose, right? If I remember correctly.
Yeah, we choose the on-chip solution.
Yes. So if you were to choose, for example, the in-pipeline one, do you think you could improve the performance or improve the resource usage a lot, or would it, would there be not that much of a difference?
So I expect the performance will grow. The resource usage depends on the encoding of constraints, but I would expect that we gain additional time when doing the in-pipeline implementation, because when you're doing the in-pipeline implementation, the signal taps can be even earlier, and they can be branch predicts. They can also implement branch prediction awareness, and there you have the full time and full flexibility. And as we have shown, time is what is required, what is crucial here, and to block the attack. And I think we would gain additional time and therefore increase performance. But as part of our future work, we are also working on improving our way of signal tapping in the early pipeline stages. And we are also thinking about improving this on-chip solution.
Okay. Do you have, could you guess how much it would improve? Is it like, would it improve 5%, 10%, 50%, or could you make the overhead almost nothing, or what do you think?
So the runtime overhead, I would expect it to depend well on the choice here, but also on the encoding. And I'm working on a solution to have zero overhead, but I'm not sure whether that will be feasible.
Okay.
So when you have enough time here and you have a good encoding and the memory lookup is fast, and you say you have the common case is fast, maybe that runs with zero overhead, but I'm not sure about that. We will try that.
Okay, well, thank you.
Thanks for your question.
So thanks
You're
again.
welcome.
And now we have our last presentation of this session and also of this year workshop. So if the author, Oya, if I pronounce it correctly, could you join us?
Yeah, I'm here. Can you hear me?
Yes. So Buya received his bachelor in electrical engineering and master science in computer architectures, and he is currently a PhD student in the ECE department of University in Victoria, Canada. He's studying electrical engineering, focusing on deep learning, and his research interests include machine learning and parallel high performance computing. And we would like to hear your presentation about some fancy neural networks.
Okay, can you see my screen and hear me well?
Yes.
All right. Hello, everyone. Thanks for having me here. This is Fritjof. I'm going to talk about convolutional fully connected capsule network. This slide is a summary of our work, so it includes everything that we did in this research. In this work, we're optimizing the new generation of classifiers called capsule. Sorry?
Ami m'a demandé si tu réponds.
I think your microphone is on. Okay. So we are going to optimize a new generation of classifiers called capsule networks. Capsule networks have several advantages and disadvantages compared to convolutional neural networks. The advantages include that they're better at detecting images that have overlapping classes inside them, and they're also performing better on affine transformed images. But the disadvantages include, one of the disadvantages is that they're very slow due to their different structure, and the fact that they have a high number of capsules. So here we are presenting CFC CapsNet, convolutional fully connected capsule network, that includes a new layer. We introduce a new layer called CFC layer, and we also optimize the decoder, which is the reconstruction part of the network. So the CFC layer aims to summarize the extracted features to capsules. And in the decoder side, we're using deconvolution instead of the fully connected. I will talk about it in detail later. And the key results on CFAR 10 dataset are we have 4 times faster inference, almost half, we have reduced number of parameters to 50%, and we have 1.46% improvement in the accuracy. So this is the outline. I'll talk about the capsule network, an introduction to them, and then I'll introduce a CFC layer, and I'll talk about the CFC CapsNet, our solution, and then we have the results and the conclusion. So capsule networks are the new generation of classifiers after convolutional neural networks. They're better for detecting images with affine transformations. It means if you basically train them on the normal images with no transformations, and then you test them against images that have some sorts of affine transformations applied to them, it works relatively good compared to CNNs. The other thing, the other advantage for CapsNet is that they're better for images containing overlapping classes. So a single image containing several classes, they can detect these type of images better than CNNs. But CapsNet has its drawbacks. It's slow due to the new structure, which is the structure of neurons as capsules, and it's relatively and it has a relatively low accuracy. And on the bottom, you can see the architecture of capsule network that I will explain a little bit in the next slides. So the computational unit in capsule network are vectors or capsules versus neurons in CNNs. As you can see at the image in the bottom, CapsNet has a simple feature extractor that extracts low-level features using 2 convolutional layers. And then the output of this feature extracted is reshaped to vectors. And the vectors are then multiplied with a matrix. And then we have the primary capsules. And then we have the secondary capsule layer. And the way the capsules are inferred from the previous layer to the next layer is done using an algorithm called dynamic routing. And so once we have the secondary or output capsules, we can do the classification based on this result. So the output, the final output of the capsule network is the output capsules, which it has one vector for each class. The magnitude of each vector shows the probability of existence of an object of that class. And the other thing that CapsNet provides, well, compared to CNNs, is that each dimension of these vectors are meaningful. So basically, ideally, each of these dimensions correspond to one instantiation parameter, like pose, deformation, and etc. And finally, as you can see on the image in the bottom, there's also a decoder to reconstruct the input images. And this is, I will explain in the next slide. So this is the decoder used in the original CapsNet implementation. So this decoder tries to reconstruct the input image, and then it compares the reconstructed image with the input image, and it creates a new term in the loss function. This is done for regularizing the training process. This decoder is based on fully connected layers in CapsNet. So now we'll talk about the CFC layer, or convolutional fully connected layer. In the CapsNet, as I explained, the feature extractor output is reshaped to capsules. There are too many capsules, like for the MNIST dataset, there are 1152 capsules. And dynamic routing takes a long time and a lot of resources to process that many capsules. So as you can see on the image in the bottom, we have one convolutional layer, and then the second convolutional layer is reshaped to vectors or primary vectors or capsules. So basically in a way that this 256 feature maps, each 8 of these feature maps are grouped in a manner so that we have these 8-dimensional vectors extracted from the second convolutional layer, basically by reshaping it. But here, we propose this CFC layer that creates the capsules in a different manner. So as you can see on the figure on the right, each spatially correlated region creates a single capsule. So basically, we are taking all these blue regions and then connecting all of them, flattening them, and feeding them to a single fully connected layer to create a single capsule, single vector like this. So all these blue regions get just one vector, and all the yellow region gets one single vector. And this is like strided, just like how the convolution operation is performed. So basically, we can say the CFC layer is a convolutional layer, but it doesn't have the weight sharing property because we have different fully connected layers for each spatially correlated region. Using this method, we produce significantly fewer yet more powerful capsules because this network leads to a higher accuracy, as I will explain later. So there are two parameters for the CFC layer. The first parameter is the kernel size, K, and the second one is the output dimensionality of each vector that we create, D. CFC CapsNet includes the integration of the CFC layer right after the feature extractor. Also, we optimize the decoder. We changed the conventional decoder of CapsNet, which was based on fully connected, to work using deconvolutional layers. And also, we are making it class independent. Basically, in the previous method, the output capsule, the incorrect output capsules were masked using zeros and then fed to a fully connected, to several subsequent fully connected layers. But here we are only taking the correct output capsule. This makes it class independent. And we're just taking the correct one and feeding it to a fully connected layer. And then we reshape it to the 3D shape of the feature maps, and then we have subsequent deconvolutional layers to reconstruct the image. So deconvolution is more powerful than fully connected in terms of the reconstruction, and it also results in fewer number of parameters. So let's talk about the results. In this table, you can see the accuracy and the number of parameters for our approach on different data sets, MNIST, Fashion MNIST, C410, and SVHN. You can see so basically MNIST and Fashion MNIST share the same data structure. The same is true for C410 and SVHN. For this reason, they have the same number of parameters. MNIST and Fashion MNIST both have 8.2 million per number of parameters, but we reduce this by 30% and we get 5.7 million parameters. And for C410 and SVHN, we get almost 50% reduction in the number of parameters. And in terms of the accuracy is almost the same for MNIST, almost no change. For Fashion MNIST and C410, we get almost 1.5% increase in the accuracy. And for SVHN, we get 0.6% increase in the accuracy. So let's talk about the testing and training times. So on the left, you can see the network testing time. And on the right, you can see the network training time for different data sets, MNIST, FMNIST, C410, and SVHN. As you can see on the left, the training is almost 4 times faster on the CFC CapsNet compared to CapsNet. And it's almost 4.5% faster during the inference testing. The testing is on the left and the training is on the right. So for example, if you take a look at the C410 testing time, you can see that the time is reduced from 19.89 seconds to 4.17 seconds, which is a significant improvement in terms of the network speed. And for the training, you can see that for C410, it took 228.78 seconds, and it was reduced to only 50 seconds for the training. So this is a significant increase in the network speed overall. So we introduced CFC CapsNet. CFC capsnet includes the introduction and the employment of the CFC layer. We also optimize the decoder and change the structure from fully connected layers to deconvolutional layers. We have a significant reduction of number of parameters, like 50% for CFR10, and the network is substantially faster. It's 4.5 faster inference for CFR10, and it also has marginally higher accuracy, 1.46% increase in the accuracy for the testing of on a CFR10 dataset. So that's it, and I'm here if you have any questions.
Thank you very much.
You're welcome.
So are there any questions?
Okay, I can see a question in the question and answer. It's asking about the framework we use for the implementation. We use the PyTorch implementation in this work.
And is this code open source like the rest of this paper question?
Yes, yes, it's open source. And also I have put the code of this work on GitHub. If you just search for CFC capsnet, you can find the code.
And I have a question. How far do you think you can extend this approach? Because you presented it on, well, let's say, rather compact or rather simple examples like NIST, fashion NIST, etc. But can you scale it up to more complicated classification tasks, for example?
Yeah, so yeah, that's a very good question. The problem with capsule network is due to its structure, it cannot be yet applied to large scale images with high number of classes. And the reason is the number of parameters explodes as the dataset gets more complicated. And basically it has a kind of limitation on the image size for now. But basically, the next thing I'm going to do is to try using the CFC layer on other variants of capsnet, because we have other, basically in this work, I just implemented on top of the original implementation of the capsnet, but we can look for like better implementations and more powerful implementations of capsnet and try integrating the CFC layer to those works to see how it works.
Thank you.